because it's much more fluid, but it is also much more challenging in the way it forces us to look at things differently. So we hope you'll enjoy the speakers and the sessions we've lined up today, so that the energy sector in Ukraine can benefit from learning this and seeing how it can be adaptation can be added to existing mitigation plans and to the challenges, and to help frame and address the challenges that the sector itself is facing. So thank you, and I hope you enjoy.
Yeah, we always enjoy to talk with you. It's very nice. Dear colleagues, я хотіла ще раз звернути увагу, може хтось не помітив, що у нас іде автоматичний переклад, верніше синхронний переклад, то, будь ласка, виберіть канал, який вам зручно слухати, чи англійську версію, чи українську. Зверніть, будь ласка, на це увагу. Так, і наступний наш спікер – це Михайло Чиженко. Михайло, ви вже з нами?
Так, доброго дня. Доброго дня. Мене чутно?
Так, зараз чутно. Михайло Чиженко, Міністерство захисту довкілля та природних ресурсів. Раді вітати вас.
Я багато часу не займу, особливо після виступів пана Торстена і Андерсена, де фактично вони все сказали, що можна було з цього приводу сказати, то я тільки додам декілька речей. Ну, перш за все, отой парасольковий документ, про який згадував пан Андрес, а саме стратегія екологічної безпеки та адаптації до зміни клімату, яку зараз розробляє широке коло фахівців, вітчизняних, закордонних. Сьогодні була оприлюднена серед членів робочої групи. Завтра буде засідання робочої групи. Тут на цьому вебінарі присутня більшість членів цієї робочої групи. Тобто в нас завтра буде таке обговорення цього документу, що дуже є важливим. Знову ж таки, повністю підтримуючи те, що сказав пан Андрес в своєму виступі з приводу тих прогалин і того подальшого шляху щодо розроблення дій, планів, політик з адаптації до зміни клімату, ця тема, ну, скажімо так, в Україні не є такою просунутою, як, скажімо, політики і заходи щодо пом'якшення зміни клімату. Тому ці семінари, сьогодні буде перший секторальний семінар, і саме ми починаємо з сектору енергетики, є дуже важливими для нас. І я дуже сподіваюся, що ми отримуємо ті знання, той досвід, який допоможе нам не тільки зараз при підготовці цих парасолькових документів, але і розробленні відповідних планів заходів або планів дій на виконання цих документів, а також подальших секторальних політик та заходів, які будуть розроблятися. Тому ще раз вітаю всіх учасників. Дуже приємно бачити сьогодні на цьому засіданні аж 68 учасників. Сподіваюсь, наступні 5 вебінарів, які ми запланували, будуть також такими ж багаточисельними. Ну і, як то кажуть, до роботи і всього найкращого всім хочу побажати. Мені дуже самому цікаво прийняти участь сьогодні в цьому семінарі і дуже корисно, я думаю. Дякую.
Так, дякую вам, Михайло. Дійсно, хотіла сказати, що з кожним разом у нас стає все більше і більше. Вже нас 69, тому сподіваємося, що ще колеги приєднаються. А так, тепер має виступити перед нами Олександр Тарасенко, міністр енергетики України, з оглядом енергетичного сектору. Олександре, ви нас чуєте?
Так, доброго дня.
Доброго дня. Вітаємо.
Я маю презентацію невеличку, зараз спробую її запустити. Так. Угу.
Так, вже добре бачимо.
Так. Єдине, що я відповідаю за сферу європейської інтеграції, європейської євроатлантичної, тому буду говорити саме про наші пріоритети в цій сфері. Так. Ну, по-перше, в європейському зеленому курсі, на який ми наразі орієнтуємось, підкреслено необхідність розвитку енергетичних ринків з окремою увагою до розроблення інтегрованих планів з енергетики та клімату. Для цього ми працюємо над розробкою інтегрованого плану з боротьби зі зміною клімату та розвитку енергетики до 30-го року. Перший проєкт інтегрованого плану буде представлений вже у цьому місяці. Він готовий, наразі перекладається на українську і буде після цього обговорюватися. Наразі здійснено аналіз наявних цілей, політик та заходів у стратегічних документах України, які доцільно включити до цього плану. Оновлено модель розвитку енергетичного сектору України та триває її узгодження з моделлю, що використана для розробки другого національного визначеного внеску України в рамках Паризької угоди. Паралельно здійснюється робота по перегляду енергетичної стратегії України з урахуванням викликів, що ставить перед нами європейський зелений курс. Нова енергетична стратегія, розробка якої розпочнеться вже в найближчі пару місяців, матиме горизонт планування до 2050 року та буде враховувати прагнення України досягти кліматичної нейтральності. В рамках реалізації діючої енергетичної стратегії значна увага приділяється реформуванню енергетичного сектору та, зокрема, здійсненню важливих реформ ринків природного газу та електричної енергії і запровадження законодавчого регулювання на основі законодавства та практик ЄС. Під час реалізації енергетичної стратегії важливо забезпечити безпечну, конкурентоспроможну та стабільну роботу енергетичної системи шляхом проведення якісної реформи енергетичної галузі при одночасному зниженні вуглецеємності економіки в цілому. У цьому контексті необхідно відзначити прагнення України системно здійснювати заходи з підвищення енергоефективності та розвитку відновлювальної енергетики. Для цього розроблено національний план з енергоефективності на період до 30-го року. План спрямований на досягнення національної мети з енергоефективності відповідно до вимог директиви ЄС про енергоефективність. Міністерство працює також над розробкою та доопрацюванням, вже можна сказати, концепції реформування вугільної галузі, яка стане однією з складових концепцій трансформації вугільних регіонів. Ми вбачаємо значний потенціал розвитку співпраці з ЄС у цій сфері, результатами якої може стати реалізація пілотних проєктів з трансформації вугільних регіонів, залучення інвестицій та створення нових робочих місць. Також Міненерго розглядає можливість розробки дорожньої карти розвитку сфери виробництва та використання водню в Україні з урахуванням міжнародного досвіду та стандартів. Наша країна має великий потенціал виробництва чистої енергії і визначена одним із потенціальних партнерів ЄС щодо виробництва та постачання водню у водневій стратегії Європейського Союзу. Решта наших пріоритетних реформ деталізовано в секторальних стратегічних документах, зокрема щодо розвитку ядерної енергетики, газовидобування, синхронізації з НЦІ тощо. Значна частина цих документів буде актуалізована найближчим часом на базі цих основних документів, про які я вже сказав. Енергоефективність для нас – це не лише ключ для розвитку економіки, а й до кліматичної нейтральності. Адже модернізація електричної інфраструктури та новітні технології в генерації електроенергії принесуть колосальні результати як в економії енергоресурсів, так і в підвищенні надійності енергопостачання. Це все призведе також до покращення стану довкілля, а чисте довкілля – це чисте повітря для нас і здоров'я українців. Важливим напрямком є підвищення енергоефективності в паливно-енергетичному комплексі. У нас дуже високі витрати в електричних мережах. Наразі міністерство завершує розробку концепції Smart Grid технологій, і я вбачаю перспективу співпраці з ЄС при модернізації мережевої інфраструктури та реалізації проєктів з підвищення ефективності передачі електроенергії. Важливим також є заплановане ухвалення нового закону України про енергетичну ефективність, направленого на імплементацію директиви 2012-27 про енергоефективність. Проект цього закону зареєстровано у Верховній Раді 12 грудня минулого року. Відповідно до цієї директиви, на її виконання, ми також розробили національний план з енергоефективності до 30 року із встановленням відповідних національних цілей з енергоефективності. Проєктом цього національного плану передбачено скорочення кінцевого споживання електроенергії на більш ніж у 17% зі звичайним прогнозованим споживанням. Перевагою цього плану є поступальність, адже окрім загальної цілі на 30 рік визначаються проміжні індикативні показники на 21, 25 та 30 роки. Такий підхід дозволить відстежувати ступінь досягнення цілей для виконання наших міжнародних зобов'язань. І, можливо, дозволить одразу коректувати якісь показники і нашої стратегії. Крім того, з метою відновлення функціонування та стимулювання подальшого розвитку енергосервісу у парламенті зареєстровані два проекти законів України. Ці законопроекти спрямовані як на вирішення оперативних питань щодо розблокування закупівель енергосервісу, так і забезпечення подальшого розвитку зазначеного інструменту шляхом посилення гарантій замовників і виконавців, збільшення можливостей для залучення інвестування, а також розширення сфер застосування на об'єкти теплопостачання, централізованого водопостачання та водовідведення, розподілу електричної енергії та природного газу. Також необхідно зазначити про те, що 23 липня 2020 року вчинено угоду про внесок між Україною та Європейським банком реконструкції та розвитку щодо участі України у фонді Східноєвропейського партнерства з енергоефективності та довкілля E5P. Участь у цьому фонді дозволить отримати доступ до фінансової підтримки у вигляді грантів та технічної допомоги для реалізації проєктів з підвищення енергоефективності та поліпшення стану довкілля, результатом яких має стати значне скорочення споживання електроенергії, зменшення викидів вуглекислого газу та інших парникових газів в Україні. Україна впроваджує систему енергетичного маркування та встановлення вимог екодизайну енергоспоживчих продуктів відповідно до оновленого законодавства ЄС. Це робиться для покращення енергетичних та екологічних характеристик енергоспоживчих продуктів та зменшить рівень енергоємності валового внутрішнього продукту, який наразі в 2-3 рази більший, ніж в країнах ЄС. Наразі розроблено та затверджено 38 технічних регламентів, з яких 23 з екодизайну та 15 з енергетичного маркування. Наказами Міненерго затверджено 11 переліків національних стандартів для відповідності вітчизняного обладнання основним вимогам технічних регламентів ЄС. Щодо відновлювальної енергетики. Загалом ми маємо позитивну динаміку виходу України з кризи в енергетичному секторі, що була спричинена коронавірусною хворобою та прорахунками минулих років у питаннях розвитку ВДЕ. При цьому ми дотримуємось високих стандартів прозорості прийняття рішень та виконання міжнародних зобов'язань навіть у таких непростих умовах. В Україні було прийнято важливий закон, який імплементував підписаний меморандум з виробниками зеленої енергетики. Це дозволило не тільки врегулювати кризу, що виникла в сфері відновлювальної енергетики, але й зберегти партнерські відносини з інвесторами. Зі свого боку, можу запевнити, що ми будемо всебічно підтримувати компанії, які мають намір інвестувати в Україну. Після набрання чинності зазначеного закону рівень розрахунків гарантованого покупця значно покращився. Зокрема, в серпні-вересні склав 100%, у жовтні близько 80%. При цьому міністерство докладає максимальних зусиль для забезпечення 100% оплати на постійній основі. На жаль, наразі цей відсоток є нижчим, що спричинено ціновими диспропорціями, які існують на ринку. Також одним із пріоритетів роботи міністерства є забезпечення погашення заборгованості перед інвесторами, що утворилися до укладення меморандуму та має бути погашена відповідно до графіку. В Україні за підсумками 2020 року частка ВДЄ з великими ГЕС очікують становитиме на рівні 12%, а відповідно до прогнозного балансу на 2021 рік ця частка має зрости майже до 14% або 20 мільярдів кВт-годин. Нашою поточною енергетичною стратегією передбачено досягнення до 2035 року частки ВДЄ у виробництві електроенергії на рівні 25%. Вважаю, що ця ціль є абсолютно досяжною, оскільки зараз ми рухаємось по випереджаючій траєкторії. Є чітке бачення, як забезпечити подальший сталий розвиток відновлюваної енергетики у нашій країні. Міністерство, уряд в цілому спільно з НЕК «Укренерго», регулятором, гарантованим покупцем вживають всіх необхідних для цього заходів. Міністерством було підготовлено максимально компромісне рішення щодо розмірів квоти та графіку проведення аукціонів, яке врахує стан та динаміку розвитку галузі, визначене енергетичною стратегією цільових показників в сфері ВДЄ, очікуваний попит на квоти, а також технічну спроможність енергосистеми інтегрувати нові потужності з негарантованим графіком виробництва електричної енергії. Загальна потужність, що пропонується до розподілу на аукціонах в цьому році, складає 365 МВт, з яких ВЕС 150 МВт, СЕС 155 МВт, включаючи регіональну квоту та квоту для малої розподіленої генерації. По іншим видам це біомаса, біогаз, малий ГЕС 60 МВт. Водночас показники річних квот на 2022-2025 роки є індикативними та можуть бути переглянуті з урахуванням таких обставин. Це фактичні результати аукціонів цього 2021 року, зокрема попиту на квоти та кінцеву ціну за кіловат-годину зеленої електроенергії, стану будівництва об'єктів нової високоманеврової генерації, актуалізація показників енергетичної стратегії з урахуванням цілей, які нам задає Європейський зелений курс, законодавчого регулювання роботи систем накопичення енергії в ринку електричної енергії. Проведення перших конкурсів на будівництво високоманевреної генерації очікується вже в цьому році. Щодо розвитку водневої енергетики. Міністерство енергетики підтримує розвиток водневої енергетики та вітає ухвалення водневої стратегії ЄС і започаткування Європейського альянсу з чистого воду. Водень, які виробляють за допомогою відновлюваних джерел енергії, один із ключових елементів стратегії ЄС щодо вирішення проблем зміни клімату та розвитку сталої енергетики. Оскільки ми прагнемо до досягнення тих же цілей, ми маємо рухати в мейнстрім. Зниження вартості ВДЄ сприятиме росту популярності зеленого водню та зменшенню викидів викопного палива приблизно на третину за нашими розрахунками. Все це залежить від координації наших політик та відповідних політичних рішень. Міненерго розглядає можливість розробки дорожньої карти розвитку сфери виробництва та використання водню в Україні з врахуванням міжнародного досвіду та стандартів. Дорожня карта представить потенціал розвитку внутрішнього українського ринку водневої енергетики, перспективи використання водню у транспорті та відповідну екологічну оцінку. Наступний крок – це буде розробка концепції розвитку водневої енергетики до 50-го року, законодавчі ініціативи, розробка технічних регламентів та стандартів. Наша країна має великий потенціал виробництва чистої енергії та визначена одним з потенціальних партнерів ЄС для виробництва та постачання водню до Європейського Союзу. Наразі ми ініціювали розвиток досліджень даної сфери та для вирішення ряду питань, зокрема перегляду нормативно-правових актів для забезпечення розвитку водневої енергетики, а також технічних питань щодо виробництва, транспортування водню, його використання в різних сферах, а також безпеки під час транспортування та зберігання. Для забезпечення транспортування відновлювального водню до ЄС ми вважаємо і зараз проводимо дослідження на цю тему, можна буде використовувати потужності української ГТС. Це питання опрацьовується для визначення відповідних маршрутів та комплексу заходів щодо забезпечення надійності та безпеки роботи ГТС. Відповідно до цілей енергетичної стратегії до 2035 року, середньорічне виробництво зеленого водню може скласти 5,5 мільярдів кубометрів. При цьому Україна має значний енергетичний потенціал ВДЕ, це за нашими розрахунками до 537 ГВт, та еквівалент електролізу зеленого водню 337 мільярдів кубометрів водню. Це за базовим сценарієм Інституту відновлювальної енергетики НАН України. Щодо інтеграції до європейських ринків. Наразі продовжується робота по створенню повноцінних ринків природного газу та електроенергії та здійснюються заходи для повної інтеграції у європейську систему транспортування газу та інтеграції української енергосистеми в європейську енергомережу НСЕ. Наразі здійснено вже інтеграцію з НСГ шляхом переходу на добове балансування. Подальшими кроками у співпраці з європейською мережею операторів газотранспортних систем буде гармонізація законодавства, узгодженість процедурних умов, дотримання принципів відкритості та гарантування безпеки постачання газу. З 1 серпня 2020 року в Україні втратила чинність норма про спеціальні обов'язки учасників ринків щодо постачання газу населенню. З цього часу для домогосподарств почав діяти повноцінний ринок газу. Зараз він трошки обмежений прайскепом, але це тимчасова міра і це, я думаю, не буде повторюватися. Також інтеграція до НСЕ – це проєкт національного значення, в тому числі з точки зору забезпечення національної безпеки, оскільки процес інтеграції передбачає від'єднання об'єднаної енергосистеми України від енергосистеми Російської Федерації та Республіки Білорусь. Тому стратегічною метою залишається здійснення усіх необхідних заходів для пришвидшення роботи по приєднанню до енергосистеми ЄС НСЕ, що у результаті завершить процес створення прозорих та конкурентних енергетичних ринків з ефективними механізмами захисту вразливих споживачів. Для цього буде забезпечено повну відповідність нормативно-правової бази України первинному та вторинному законодавству ЄС з метою забезпечення прозорості, чесності основних гарантій ринку, верховенства права, в тому числі захисту конкуренції. Для виконання умов інтеграції в НСЕ в частині завершення процесу сертифікації Укренерго компанією було подано заявку на сертифікацію щодо відокремлення та незалежності оператора. Вирішення цього питання потребуватиме внесення змін до Закону України про ринок електричної енергії щодо сертифікації ОСП за моделлю Independent System Operator. На сьогодні виконано практично всі технологічні заходи з підготовки, зазначені в угоді про умови майбутньої синхронізації з НСОЄ, яку підписано було в 2017 році. Наразі проводиться випробування генеруючого обладнання електричних станцій для моделювання та валідації систем збудження та систем регулювання частоти та потужності. Ця робота продовжиться синхронно з Республікою Молдова. На сьогодні маємо відчутні результати. Зокрема, проведено низку досліджень, тестувань систем збудження на енергоблоках АЕС, а також на ТЕС, ТЕЦ, ГЕС. Оновлено експлуатаційні угоди із суміжними європейськими системними операторами, що є обов'язковим для інтеграції. Розпочато роботи з реалізації проєктів будівництва нових об'єктів для забезпечення надійного електропостачання споживачів прикордонних районів. Це необхідно для відокремлення об'єднаної енергосистеми від енергосистем Білорусі та Російської Федерації. Наступний важливий етап – це робота об'єднаної енергосистеми України в ізольованому режимі. З огляду на те, що я сказав раніше, Україна прагне достроково виконати свої зобов'язання щодо повної інтеграції, яке зараз заплановано на 2023 рік. Дякую за увагу.
Так, дякую вам, Олександре.
Так.
Дуже цікава і об'ємна доповідь. Наступний спікер – Лорета Станкявічуте, Міжнародне агентство з атомної енергії, адаптація до змін клімату та важливість в енергетичному секторі. Лорета, hello.
Hi, hello.
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 Yes, we hear you now.
That's good. Good start.
Nice to see you with us.
Nice to see you too. So many thanks for inviting IAEA, International Atomic Energy Agency, to participate in this event. So we will gladly share with you the experiences with you on this topic, on this very important topic, and we'll offer our support in the future in case needed. So I will share the presentation now. Just a second. Can you see it well?
Yes, we see it very well now.
Okay, great. So this presentation will draw, let's say, a lot on the report that was published by the agency several years ago on the climate change vulnerability and adaptation in the energy sector. It will be, I would say, more, let's say, more general presentation, but certainly we could tailor it after all in discussions into more, let's say, Ukraine and context. Yes. So I will just continue. Yeah. So basically, in general, to enable, let's say, better response measures to be designed to climate change impacts, yeah, these impacts are discussed separately, namely those that manifest as so-called gradual climate change impacts, which have long-term consequences, and extreme weather events that impact more in a shorter term. So these gradual climate change are changes in climate properties, let's say their statistical means or their variability, and they persist usually, as I said, over a prolonged period of times, typically longer than decades. And as you know, climate change is projected to increase global mean temperature and affect most other attributes of the Earth climate, such as precipitation, its seasonal distribution, windiness, sea level rise. Most of, let's say, global and regional climate models forecast changes of these attributes, although there is a, let's say, considerable degree of uncertainty both in the magnitude of projected global changes and especially in the regional patterns of these changes. Yes. So also changes, let's say, in the characteristics of various extreme weather events, such as increasing frequency, intensity, duration, or even spatial extent of heat waves, droughts, storms, and so on, are also forecasted in these models. And all these changes will trigger considerable impacts for the energy sector. So climate change can affect all the energy supply chain, from resource extraction to transmission and distribution, yeah, passing through transport and conversion, let's say the power generation itself. So, for example, hydro generation may benefit, suffer, or both from changes in the rainfall. We know that. Wind generation may also be impacted by local adjustments to the wind regime. Low-lying, let's say, coastal or offshore infrastructures may be impacted by extreme weather events such as hurricanes, sea level rise, potentially disrupting production and affecting, let's say, structural integrities. A temperature change may alter the generation efficiencies, and in particular induce cooling water efficiency decreases of all thermal power plants. That is fossil fuel, nuclear, biomass fired, or even concentrated solar power plants. Yeah. So this publication explores diverse range of impacts, as I said, on the energy sector, resulting from these gradual climate change and extreme weather events, and explores ways to counter those impacts, yeah, in a systematic way for all the elements of this supply chain mentioned, such as I said, extraction, transport, conversion, transmission, and distribution. So starting with the first step in the energy supply chain, that is, let's say, extraction, resources related. So these are sort of several examples where we could find these vulnerabilities to climate change. So, for example, vulnerability of coal and uranium mining to extreme weather events depends basically on the type of mining. Yeah. So open cast minings can be affected by extreme precipitation and related floods, as well as erosion. As an example, like in 2001 and 2012, there were floodings of thorough energy mines in Australia that even slightly affected the price of uranium. Speaking of oil and gas extraction, a large volume of these infrastructures operate in cold climates. So higher mean temperatures can actually melt the frozen ground, and thus this thawing of so-called permafrost can severely affect oil and gas facilities by disturbing their foundations, breaking pillars and pipes. Gradually increasing sea level rise might also affect offshore platforms by adjusting to even relatively high rates of sea level rise. This sort of vulnerability seems to be manageable, though. For wind, depending, let's say, on the location, extreme wind conditions and tornadoes can severely damage all these oil and gas infrastructure wells as well, while sea storms and cyclones can threaten offshore platforms, and we have seen a number of examples in that area. For hydro, in general, given that let's say temperatures are projected to increase globally, evaporation on large open waters can be expected to increase. Yeah, of course, this will depend on the region. For example, this depth of loss for the Aswan High Dam, which is on the Nile River, is calculated to be even like 2.7 meters or 11% of the reservoir capacity. Yeah, so this is quite a big vulnerability, I would say. However, deep dams, let's say, with smaller surface areas would be less affected than those with large surface areas. Yeah. Another important thing is that an indirect impact of warmer conditions in many regions will involve increasing demand for water for other uses, yeah, other competing uses, especially, for example, for irrigation and agriculture, yeah. So leaving less water in rivers for hydropower generation or for other uses. So hydropower planners will need to account for these competing demands for water when assessing available resources. For wind, changes in, let's say, interannual, seasonal, and diurnal variability are quite unclear, and they likely also to differ by different locations. For solar, changes in isolation and cloudiness are the main effects of gradual climate change on the resource base, let's say, for all types of solar energy. If we're speaking of solar heating, photovoltaic, or concentrated solar power, but that technological adaptation options are possible. Speaking of transportation, let's say, to conversion points, to power plants, for example. So primary, let's say, fossil energy sources such as coal, oil, and gas can be transported in diverse ways. Yeah, it can be ocean, rivers, railroads, to distances ranging from few kilometers to 1,000 kilometers. So in the case, for example, of a sea level rise, port and dock facilities, coastal roads and rails will need to be, let's say, amended to avoid or at least reduce the damage and disruption caused by potential flooding. Yeah? In regions with declining precipitation levels, ship and barge transport in rivers might be affected by declining water levels. In regions with cold and temperate zones, changing freeze, thaw cycles might cause increasing damage to roads and rail tracks. But these adjustments in infrastructure can be made as part of the, let's say, regular maintenance repair cycles. Pipelines, as you know, play a central role in the energy sector by transporting oil and gas. Pipelines have been operated for over a century in diverse climatic conditions on land, from hot deserts to permafrost areas, and increasingly even at sea. Yeah? So this implies that technological solutions are available for the construction and operation of pipelines under diverse, let's say, geographical or climatic conditions. Yet, changing climate and weather conditions may require adjustments in existing pipelines and improvements in the design and deployment of new ones to deal with extreme rains, high winds, and storms. For example, above ground sections of pipelines can be affected by extreme high and low temperatures through material damage and thermal expansion or contraction. Extreme rain events can also damage underground pipelines by basically opening them, unearthing them, yeah, leaving them open on the earth. Yeah. So what's the vulnerability of, let's say, thermal power plants to gradual climate change? Yeah. So electricity generation at thermal power plants is directly impacted by high and low ambient air temperatures. Yeah. So, excuse me, I think okay. I'm sorry, I missed. Yes, that's the right slide. I'm sorry. So basically, what I was saying that electricity generation at thermal power plants is directly impacted by high and low ambient air temperatures. So higher mean temperatures reduce the thermal efficiency of all thermoelectric plants. Yeah, according to estimates, a rise in ambient air temperature of about 1 degree Celsius would reduce the thermal efficiency by some 0.1 to 0.5%. And the total capacity loss accounts for 1 to 2% per 1 degree higher air temperatures, including decreasing efficiency of cooling processes and reduced operational times, for example. There is no really adaptation option to accommodate these higher mean temperatures for existing power plants. For new builds, site selection where possible should be in cooler climates. At the same time, ambient temperature would be let's say, only one of dozen of factors that affect the setting, many of which would have probably greater influence on siting decisions. Changing precipitation patterns induced by climate change could also lead to long-term reductions in the water levels of rivers or lakes that provide cooling water for inland existing power plants, which could pose, as you know, serious problems. Yeah. In areas where, let's say, long-term rainfall patterns will reduce water availability, power plants could also, as I mentioned, compete with many other vital uses for scarce water. Could be, as I said, agriculture, but could be also industry, households. In such situations, generation from power plants maybe even need to be curtailed or halted if water levels are too low. Yeah. The adaptation options here depends really on the cooling techniques used. As you know, there are several of them, mainly big categories is between the once-through techniques and the recirculating cooling systems. For the plants near the coast, more persistent wind can, for example, over time carry additional salt sprays to those plants, and that salt deposited on exposed cables and metals can lead to faster corrosions and potentially to short circuits if the deposits are not cleaned regularly. So for this, basically increased maintenance and appropriate shielding and seals could be effective solutions. For the sea level rise, plant owners or regulators should consider doing the type of coastal vulnerability and sea level rise analysis. For existing power plants that are found to have a high level of vulnerability during the life of the plant, the primary option for adapting to sea level rises is basically to build dikes and retaining walls and other earthworks to prevent storms surges from reaching it. Thermal power plants are also subject to diversity of extreme weather impacts, making them vulnerable if not adapted. Yeah. And as climate change occurs, past events might not be sufficient to predict the severity of future events. Thus, existing thermal power plants may be vulnerable to these events, and future thermal power plants, their siting and design must account for a change in climate. Yeah. For example, nuclear accident at the Fukushima site was not climate or weather related, but it highlighted basically the vulnerability of nuclear power plants to events that were not considered in design and construction. So here in this slide, we see a list of, let's say, potential extreme weather events impacts on thermal power plants. So for example, high water temperatures due to extreme heat or low water levels due to drought can diminish again plant's cooling, exacerbate this plant's cooling capacity, or can cause it to let's say violate these heat standards, environmental heat standards, by discharging hot water to a river or a lake that is already experiencing high temperatures. A heat wave, therefore, can force thermal power plants to reduce generation or go offline due to regulatory limits placed. Yeah. Again, sea level rise threatens to be one of the most economically damaging climate change events. Any flooding can be problematic for thermal power plants, especially for a nuclear power plant. But sea level rise in combination with storms could lead to site inundations. It can lead to, for coal, for example, to coal stockpile drenching in the coal power plant. So vulnerable plants must ensure that in such events, water does not reach the plant, and that basically critical buildings or sites have sufficient waterproofing and appropriate pumps and the various drainage systems. Yeah. Prospective, let's say, plant owners should also study coastal vulnerability and sea level rise in the process of the site evaluation, of course. High winds and lightning have always been a threat to thermal power plants, and as these extreme weather events become more intense with climate change, the threat will rise. Typically, the greatest threat from winds and lightning is that they can disrupt power from the grid, either off-site or via the plant's own grid interconnection. And without connection to the grid for any lengthy time, at least for a nuclear power plant, it must stop generating. Yeah, but at the same time, the plant safety systems must continue to operate, and they need power to do so. Yeah. So usually diesel generators fill this gap. But anytime, let's say, backup systems must be engaged, there is a risk of larger accidents. In terms of here, just a couple of more words about nuclear energy. Yes, because in terms of, let's say, climate change impacts, nuclear has a lot, as I mentioned, in common with thermal generation. But what's important is that nuclear is a special case because of safety concerns related to extreme weather events. Yeah, one should preserve the physical protection and security of the nuclear power plant and ensure the operation of diverse, independent, and redundant safety systems. And most importantly, there is a need for long-term core cooling and for reliable electric grid. Many types of extreme weather events can cause the electric grid to go down, leaving the MPPs only with these backup diesel generators. If those generators are not well protected, the same extreme weather event that brought down the electric grid can also damage the generators and leave the plant without power to run critical safety systems, which can, in a worst case scenario, lead to a reactor damage, an accident. So these are the key systems: electric grid, water cooling, but there is also electronic control and monitoring, physical plant access, structural integrity that should be assessed as well in face of related shifts in extreme weather events. A nuclear power plant is a complex technology requiring a large number of systems to operate safely and properly. Here is some past vulnerabilities to extreme weather events in the past for nuclear. So basically, since 1980, the IAEA has maintained a database of events at nuclear plants as reported by member states, called the International Reporting System. The main purpose of this IRS is to facilitate information sharing and learning from the operating experience of all member states. So worth to mention is that only around 2% of the incidents reported in this database are weather or climate related, so a very small number. And out of this number, the big majority, 88% of all reported incidents, primarily affected only 3 major systems, that is water cooling, electrical control systems, and transmission grid. So from 1980 through 1999, weather-related events were quite, let's say, equally distributed between lightning, winds, and freezing, with a few flooding events also. The first half of the 2000s saw 2 new types of events, that is heat and corrosion. In the second half of the 2000s, over half of the reports were already heat-related, and these mainly came from Europe. Obviously, these new heat-related events suggest that climate change may already be having an impact on nuclear energy. So coming back to this supply chain, here we are talking about oil and gas refineries. Here, severe storms and flooding have made a big impact on this type of infrastructure. Several examples, for example, in 2007, a refinery in Kansas was flooded when a levee was breached. This resulted in a spillage of more than 150 cubic meters of crude oil, which contaminated floodwaters and flooded into streets, homes, and so on, and forcing the evacuation of a number of residents. Yeah. Also, hurricane strength winds and tornadoes in this area can really overturn tanker trucks and train tankers carrying oil and oil products. In fact, in US, hurricanes, let's say Katrina and Rita, exposed not only a fragile oil and gas infrastructure due to the loss of production they caused, but a weak delivery and also distribution system. There was, in the end, there was a shortage of fuel in several states. Numerous studies also indicate that lightning strikes are the natural hazard that most frequently triggers accidents in processing and storage activities. The frequency of lightning events is expected to increase, as I mentioned, with the predicted rise in the frequency and intensity of all these meteorological hazards, such as storms, hurricanes, and so on. Speaking of hydro, here extreme weather events, especially such as drought, reduced precipitation, will have certainly negative effects on water storage in dams. Yeah. Depending on the duration of the reduced precipitation, it may be possible for storage-based hydropower plants to manage their storage and maintain their normal generation of electricity over the duration of the drought. For run-of-river installation, this might, however, be an issue since they do not have this, let's say, buffering capacity. And there are many examples of interruptions in hydropower generation due to drought or reduced precipitations, in particular in Africa. Unexpected flooding, on the other side, can also affect large dams where the large loads of sediments carried by the rivers end up in the dams and lakes. Different large logs and vegetation can actually cause damage or block up the whole system. Regarding gradual climate change impacts for wind, projections of wind energy resources derived from downscaling so-called global climate models indicate that at least for Europe and North America, the multi-year annual mean wind power densities, that is basically changes in windiness, are relatively stable during this century. Yeah? In contrast, as I mentioned earlier, the interannual, seasonal, or diurnal variability is more uncertain. Yeah? And as you know, variability determines the timing of power availability. Other changes may be beneficial to the industry, for example, reducing areas where sea ice loading or turbine icing are causes for concerns, basically because of simple reason is that the climate is getting warmer. Yeah. Extreme weather episodes do not affect the resource base, but can severely impact the operation of the wind energy. In particular, here we refer to strong winds, extremely low temperatures, and eventually ice formation that can both cause structural damages. At the same time, there are studies indicating, at least for the areas in which many of the wind turbines have been installed, specifically Northern Europe and parts of US, near-term changes in extreme condition, even if they are realized, do not really constitute a major threat, let's say, to structural safety of these turbines. And if climate leads to changes in operating conditions on longer time scales, it is plausible that the industry will be able to adapt via modification of the design standards and installations of new technologies. Regarding solar technologies, here we have three main technologies: thermal heating, photovoltaic (PV), and concentrating solar power (CSP). So for CSPs, similar as for other thermal power plants, thermal and cooling efficiency declines in water-cooled CSP systems. For solar heating, average, let's say, warmer temperatures improve the efficiency of solar heating, especially in colder regions, but reduce the conversion performance of PV models, of photovoltaic models. by estimate of around 0.5% per 1 degree temperature increase for the crystallized silicon modules, which is around 80% of the global market currently, as well as thin modules. Yeah, so this means that high ambient air temperatures in situations with high direct solar irradiation can have important impact on the maximum possible power output. Yeah. Heat is also a concern. Long-term exposure to heat can cause the panel to age more rapidly, while some materials may not be able to withstand short peaks of very high temperatures. Hailstorm can cause also fracturing of the glass plate covering most PV models, resulting in direct damage to underlying materials. There are certain international standard qualification tests for crystalline silicon and thin film models to withstand those hailstones. But this also received some criticism for not really predicting lifetimes and resistance to real-world environmental impacts, because the certain factors are mostly unknown. Yeah. A side effect of strong wind is sand and dust deposition for the CSPs and PVs, which result in reduced power output. Cleaning panels and using tracking system to rotate them out of the wind are possible responses to this problem. Regarding transmission and distribution, here warmer temperatures can cause increased transmission line losses and the extension of transmission line cables. Estimates, let's say from the UK, show that in the transmission network, 8 degrees higher summer mean temperatures would decrease the capacity of overhead lines by some 3%, and of underground cables and transformers by 5%. Other extreme weather events, for example, high winds and storms, can cause, of course, mechanical damage to overhead lines, towers, poles, and substations directly, and indirectly by blowing debris against exposed grid system components. Yeah. A combination of low temperature, wind, rain, and ice storms will probably occur less, let's say, frequently in the warming world, but when they come, they could pose physical damage on overhead lines and towers, including even collapse here, caused by, let's say, excessive weight of ice buildup. Yeah. Enhanced design standards to withstand the largest projected ice and wind loading and improved forecasting of ice storms are the main options to reduce vulnerability. Rerouting lines across less exposed regions is another option to consider. So what are the, let's say, costs of not adapting? In the worst case scenario, for example, for a nuclear power plant, not adapting can lead to significant plant damage and potential release of radioactive material. Yeah. However, typical direct costs come in the form of, let's say, lost revenue while the plant is not operating, no? Or the operation is reduced, yeah, as a result of extreme weather event. For example, if we assume a price of $50 per megawatt hour, then every 24 hours that 1 gigawatt nuclear plant is shut down cost the plant owner some 1.2 million in lost revenues. Yeah. Outages also can lead to direct, indirect costs. Every time a power plant cannot be operational due to climate change effects, electricity consumer either, let's say, experiences a power outage, or consumer pays more for an alternative electricity producing technology that fills the gap. Yeah, so it depends a lot on which technologies make up the electricity mix in the country as well. If a country is, let's say, highly dependent on nuclear, an outage can lead to a wider blackout and impose substantial indirect economic costs. These costs vary considerably from country to country, as they are based principally on the economic structure, let's say, of the country. Developed countries have a higher value added from electricity generation, thus higher values of lost load. Yeah? For developing countries, they have lower value added from electricity, also lower values of lost load, but the loss would be no less significant to the economies of those countries. At the same time, an outage of one plant in most countries would not actually lead to blackout, yeah? But the potential for costly blackouts, let's say, warrants careful consideration of adaptation options. And these adaptation options can be really numerous, yes? So it really depends on technologies, and I mentioned some of them during my presentation. It can range from such as improved skills in forecasting precipitation, for example, for a better operation of hydropower plants. Yeah. Regarding, again, more specifically to nuclear power plants, examination of this IRS database reveals that for most plants which have been built to a high margin of safety with respect to external events, basically increased maintenance, new procedures, and minor physical changes are sufficient to adapt to many threats. For example, preventing like ice blockage of water intake can be as simple as diverting some hot water from the cooling system back to the area around the intake. Yeah? Preventing lightning damage can be as simple as maintaining proper grounding and burying key outside cables. The marginal cost of adapting to these type of events do not appear to be significant when compared to the cost of plant outages. Other adaptation measures can be more costly, such as raising the height of the dikes, for example, surrounding a plant to protect against storm surges, floodings. Adapting water cooling to lower water levels and hotter temperatures may, on the other hand, be very costly. If we are thinking, for example, of changing once-through technology or recirculating a cooling option to some air cooling, which is certainly definitely much more costlier way of solving this issue. So some of main messages, basically what this climate change impacts will indeed impose a new set of conditions on the design, operation, and maintenance of existing and plant infrastructure. Yeah. Some existing energy systems already take it into account in their operation adaptation measures, and some other adaptation measures can further reduce their vulnerability and increase the resilience. Yeah. It is especially relevant to think of climate change impacts when addressing, let's say, new investments in the energy sector. Yeah. Integrated, let's say, risk-based planning processes will be critical to address these impacts. Again, some words on the nuclear energy. It's a special case, yeah, in the energy sector due to the nature of the technology. There is a radiation hazard. There is need for long-term cooling, reliable grid connection. However, it has been shown that nuclear power plants are exposed and vulnerable to various types of extreme weather events, especially to extreme hot periods that increase the temperature of water bodies used for cooling. At the same time, the industry has shown resilience and capacity to adapt to these changing conditions. Yeah. Changes in climate and extreme weather event in the future will raise new challenges for the energy sector. This will raise questions on how to design, implement adaptation measures for existing NPPs and make them more resilient. The first question is always safety. Yeah? So what would be the cost of the enhanced safety measures necessary to withstand more frequent and more intense extreme weather events? The next question is whether those safety improvements and other adaptation measures are worth making with a view to the expected gains in terms of, let's say, uninterrupted generation and income generation during the rest of economic lifetime of this power plant. Yeah. So decisions are somewhat easier for new builds. The design basis in related areas will be changed in response to projected degrees of climate change and extreme weather events. This will also include various safety standards and guides, which agency prepares and publishes periodically to enhance member states' capacity to design, build, and operate NPPs to the highest level of safety. Just very final words on the projects that we've been doing in the agency in support in this area of the vulnerability of the energy sector with some member states. So this is so-called coordinated research project. So it's basically the objective was to help member states in developing, testing, and improving different analytical frameworks for identifying and assessing risk from climate change and extreme weather events, and in developing the adaptation options. And here we see an example of one of the participating country, which is Slovenia. So Slovenian team used basically a GIS tool, which is the Geographic Information Tool, to assess vulnerability of the energy infrastructure in Slovenia. In particular, the team performed a risk assessment due to ice storms on the allocation of new facilities, namely wind turbines and transmission line. Yeah. So first, the geographic scope and intensity level for the ice storms were determined based on the past data. Then this information was combined with the categories of frequency, which allowed in the end determining the sort of risk index mapping these risky areas and less risky areas across the country due to ice storms. So this risk assessment helped to identify a sitting of a power plant, of a power line out of basically two alternatives that they had in mind. Yeah. Furthermore, this mapping of risky and not risky areas due to ice storms was further combined with the information on the spatial attractiveness and environmental vulnerability to identify risk-assessed spatial, let's say, best suitability for wind farms. So in this blue map, you can see a very small dot, red dot in the middle. So in the mid north of the country. So that was identified as the most suitable area for the wind farm. So many stakeholders were involved within this project, the results of which will form basically inputs for shaping long-term investment policy of energy providers in Slovenia. Okay, there was certainly a delay of this whole slide. I'm sorry for that. These are the examples that I wanted to show on the Slovenia case. And basically, my last slide is just to say that we are also supporting in the agency supporting countries in so-called CLU integrated methodologies, that is climate, land, energy, and water, to analyze all these, let's say, complex interactions between various key resource systems, energy, water, land, and also climate change. So the idea behind this CLU framework is simple. Land, energy, and water resources systems are basically highly integrated. As I mentioned, for example, vulnerability of hydropower plants, and also competition of water, for example, for irrigation purposes in agriculture. Yeah, so this type of questions can be analyzed with this framework. Yeah, so rather than developing a new fully integrated analysis tool, this framework draws already on existing well-tested sectoral models for each of these, let's say, resources, three resources, that is energy, water, and land. Where data is basically passed between these models in an iterative fashion. Vulnerability due to climate change can also be captured. The objective of this framework is basically to capture the trade-offs and synergies to identify policies, measures, or strategies that are efficient in this so-called broader perspective. So this was my last, let's say, sort of additional slide. I will end here. So thank you very much for your attention.
Yes, thank you, Loretta, very much for analysis that you've shown and for examples of the heavy challenging situations that we face in adaptation of energy systems. Thanks, Loretta.
Thank you very much. Thank you. Спасибо.
Yeah. Hope to see you again with us.
Yes, yes. I mean, if you have any questions, I'm here. I will probably stay connected until the end. So.
Okay, thanks. Great, great. And the next speaker, наступний доповідач, це Ханс Мартін Гюссел, European Ecological Agency. Адаптаційні виклики та можливості для європейської енергетичної системи. Прошу, Hans, are you with us?
Yes, I am. Good afternoon. Thank you very much for the invitation to present at this seminar. I would like to share my screen now. Can someone confirm that the title slide is visible?
Yes, the slide is visible.
Okay. Well, once again, thanks for the invitation. One apologies in advance. I was not aware of the program of this workshop, and the previous presentation was covering in much detail a lot of the aspects that I might have also covered. So there might be some overlaps, but I'll try to limit that. I was listening into the last 10 minutes or so, and it was a really interesting presentation by IAEA. So maybe just to start very briefly, the European Environment Agency, we are an agency of the European Union. So we work both with European Union stakeholders and with national stakeholders. We have 32 member countries and 6 cooperating countries. And our main contact points are environment ministries and environment agencies. But depending on the topic, we also work with other ministries and public stakeholders. Our task is to support and inform policy development and policy implementation. And we do this by providing relevant data, indicator, and assessments. And I will today report on some findings of an assessment report we published in 2019. We also work regularly with experts across the countries through what we call the INET, the European Environment Observation and Information Network. Now, the background of my presentation today is a EA report, which is publicly available as all our publications. You can see the URL here. We published it in June 2019, and we launched it during the policy conference of the European Sustainable Energy Week, together with stakeholders from a range of European and international institutions. And the aim was, for the first time, to bring together at the European level an overview of the available information on climate change impacts on the energy system. You've heard a lot of that just before. Together with the rapidly evolving EU policy framework, which of course is not directly relevant in Ukraine, but also the activities of the most relevant stakeholders, private and public, national, European and international, and to highlight opportunities for further action. So the policy context in the EU was large investments into the clean energy transition, building of the European Energy Union, and the report was intended to support that these massive investments in the clean energy transition are also viable in a changing climate. You've seen many examples in the presentation before. I think even one of the pictures on the bottom left might look familiar, so I don't need to go into the details of climate impacts on the energy system here. Also, you're obviously aware now about the key climate drivers. Once again, we were doing a European overview, so there was limited detail that we could provide. But the key drivers indeed are temperature rise, changes in water availability, a number of extreme climate related at renewable energy potential. Now, this is just to showcase how we try to summarize information across Europe. Obviously, the Ukraine is not directly relevant here, but you'll find a detailed analysis of the main climate impacts on the different elements of the energy system, which might complement the information just earlier provided by IAEA. But I will not go into any details here, once again, because of the geographical scope. Also to highlight that obviously climate variability is not new to stakeholders in the energy sector. There's a lot of experience already in managing weather variability and climate variability, and global climate change adds basically the longer term considerations here. But in the end, the climate resilient energy system needs to be resilient to changes or extreme weather events such as lightning, and to the long-term changes such as sea level rise, which might threaten coastal power plants, for instance. Also, in this report, we were focusing on bridging the agenda between climate mitigation, which is obviously the key driver for reshaping the European energy system, and climate change adaptation. So climate change, changes in climate system are one of the key drivers for building climate resilience and for strengthening the resilience agenda, but at the same time, the energy system is changing. The rapid growth of renewable energy sources is the key factor here, and most of them are sensitive to climate in one way or the other. And on top of that, societal changes, so modern societies are increasingly dependent on a reliable energy supply, which means that the indirect costs of energy disruptions are increasing. As you've also seen before, climate change adaptation in the energy system is linked to other sustainability concerns. Here is an example for the interlinkages between energy and water, but of course, the land nexus is also to be considered here. So different low carbon energy technologies have different needs for water and land, and this is something to be reconsidered in a changing climate. So we highlight an integrated policy approach where the consideration of different societal goals, policy goals, allows to maximize synergies and to limit the adverse side effects. We provide a limited number of national examples on adaptation. And what you can see here, you don't need to look at the details of the graphs, are just examples from two countries in Southern Europe, Spain and Greece, which face water shortages, and those might increase due to climate change. And to see how the red line shows the increase in renewable energy production over time. This is a relatively short time frame, about 10 years. And blue shows how at the same time the freshwater abstraction for electricity generation has decreased in those countries. So renewable energy here, focusing on solar and wind, can improve the energy efficiency, whereas other renewables, hydropower, depending on the context, or bioenergy, can actually increase the water footprint of the energy system. Now, obviously, as European Environment Agency, our key stakeholders are ministries, public agencies, and in most, it's organized a bit differently in different countries. The direct role of the of public stakeholders in the energy system. In some countries, even power plants are owned by the state or by public companies. In others, the sector is widely privatized. But even where the most stakeholders are market actors, private companies, there's a strong role for governments in overcoming barriers to adaptation. And it's really about, let's say, bridging between let's say, the direct costs of a disruption which energy companies observe, and the indirect cost, the societal costs of a disruption which societies experience. And this was also highlighted on a previous slide by in the IAEA presentation. So there are a number of ways how governments can support that adaptation, resilience building happens at the level that is optimal or close to optimal for society, and not just for the market actors in the energy system. And this happens through policies, through information and services, in those cases where state-owned assets are involved, resilience building, direct resilience building in them, and of course mobilizing financial resources. And yeah, this overview was copied from the International Energy Agency. At this time, and still now, climate resilience in the energy system is addressed by many EU policies. Of course, they are not directly relevant for you, so I don't go into any detail. But just to highlight it, it's not one silver bullet. There's a wide range of policies that are involved here at the European level. Some of them, maybe most importantly, the EU regulation on the governance of the energy union climate action, also require planning and reporting by all EU member states, so-called 10-year plans and so-called national energy and climate plans with a 10-year horizon, long-term strategies with a 30-year horizon. So there's a lot of activity at the European national level to actually implement those changes. Also, once again, this is obviously focused on the EU, but there are many research projects that support the climate service development relevant for the energy sector. I don't have an overview on the specific geographical scope of each of them, but some of them might have a scope that is also relevant for the Ukraine. We also share in this report examples for national adaptation actions. They're really examples. We did not conduct a systematic review of all the countries. There's a simple overview, but we really encourage also learning from each countries. So we show examples of sectoral or multi-sector climate change risk assessments. We show examples of guidance material for climate change risk assessment and resilience planning. And as an example here, the most comprehensive at that time was actually from a non-European country, the USA. Examples for sectoral adaptation plans, reporting obligations for infrastructure providers, and weather and climate services. So these examples may also serve as inspiration for the Ukraine, possibly. We also share examples for so-called adaptation case studies, once again, with a scope of our EA member and cooperating countries. All of this information is available on a platform called Climate Adapt. It's the European Climate Adaptation Portal, which is hosted jointly by the European Commission and the European Environment Agency, where a lot of information can be found, including all the research projects. And once again, some of this might also be relevant for the context of the Ukraine. Now, going beyond the report, just to share some resources internationally, which you may be aware of already. And the links to all of them are included in backup slides. And I will, of course, make the slides available to the organizers, and I assume they will share them with you. So this is a study done by Uranos, sharing 10 case studies from around the world with a focus on North America and Europe on adaptation in the energy system. There are a number of activities by intergovernmental organizations, and I haven't even included IAEA here, but IEA and OECD have done a considerable amount of work and published relevant reports that are definitely relevant also for the Ukraine. There are a number of international sector organizations being active here, and maybe particularly relevant for you is the hydropower sector, where with the support also of EBRD, a climate resilience guide was published just 2 years ago. On the information side, there's activities under the Global Framework for Climate Services, which is managed by the World Meteorological Organization, which published an energy exemplar. And at the European level, we bring this further forward with the Copernicus Climate Change Service. All the data, all the information of by the Copernicus Climate Change Service is freely available to any user anywhere in the world. And while a majority of the data sets and indicators focus on Europe, it also includes access to a number of global data sets. And finally, a number of multilateral financing institutions are developing resilience frameworks for their investments. The first one was the World Bank already around 10 years ago, and then followed, for example, here by European financing institutions, and in particular the European Bank for Reconstruction and Development. Maybe as an example, I'm borrowing a number of slides from EBRD here, how they go forward. Their approach is to identify vulnerabilities, the potential impact on infrastructure, identify adaptation measures, and of course then reap the benefits of climate resilient infrastructure. And there is considerable experience also for the energy sector, and I'll highlight here the hydropower sector, which is quite relevant in the Ukraine. How this general approach is then implemented in their portfolio development. Once again, I've highlighted this guide before. I'm sure you're aware of it, so I will not go into further detail here. And to be honest, I haven't followed up on the more recent work of EBRD, but they have also a number of other work areas under development which are directly relevant for the energy sector. So let me conclude. I hope I didn't even need to emphasize, as you're already aware, the increasing need for climate change adaptation, for enhancing climate resilience in the energy system. This need exists even if climate goals are met, because climate change is not the only driver for increasing resilience. There are societal drivers. It's the driver of increasing renewables. Obviously, there are synergies as well as trade-offs between climate change adaptation, mitigation, other sustainability concerns, water use, land use. So building climate resilience should exploit synergies where they exist with other societal objectives in order to avoid maladaptation. And of course, the trade-offs need to be considered and addressed as well. Now, market actors in the energy sector should regard assessing and strengthening climate resilience as part of their core business. I believe it's no longer an add-on. And of course, now there's also considerable pressure from investors to do physical climate risk assessment, transitional climate risk assessment. So it's part of the core activity. But governments do play an important role facilitating socially optimal levels of adaptation in the energy sector to address the direct, the indirect costs of supply failures. And a number of international organizations can provide relevant resources for that. With this, I would like to thank you, and I'm happy to take any questions if there is time for that.
Thank you very much, Hans Martin. Thank you for the valuable links, and we would be happy if you could share this presentation and the links, because we have the long road ahead I mean, the Ukraine has the long road ahead to start this adaptation process. So thank you very much. And now, dear friends, dear colleagues, do you have any questions to Martin or to Loretta? Because after that, we will have a break. It seems to me that we will put the questions till the end of our discussion. If you can join us and you can stay with us till the end of this webinar, Hans and Loretta, because the end is at 4 p.m. after Kiev. Is it possible for you to stay? Then we are waiting for you. And now we will have a break till 2:30. And that would be nice to see you again.
Thank you.
Thank you very much. Thank you.
Thank you.
Дорогі учасники, шановні друзі, ми зараз маємо перерву до 2:30. Повертайтесь. І зараз у нас ще все ще лишається майже 70 людей. Я сподіваюся, що зустрінемось в цьому ж складі після перерви. Дякую вам.
So, good afternoon, шановні друзі. Let me explain our problem in my country. It's Armenia with a very unstable weather. At the moment, the outdoor temperature in year 1 plus 15 degrees, but we expect it for tomorrow -2, -3. In this case, we should take a big attention for discussing the matter. Of course, the climate change is the problem for every country. And let me remind you that Armenia joined to Paris Agreement, and you can see our national determined contribution. And it's not all, but it's a main data. And of course, we are going to develop.
Ruben, we can't see your presentation. Share your screen. Share your screen with. You should be able to share your screen now so that people can see it.
I'm sorry. Just a minute. I'm sorry. It's okay now?
Wait a minute. Yeah. But well, now
put it in slide mode. Yes. Put it in slide mode. Exactly.
Just a minute. Okay.
Yes. Thank you.
So let me repeat it. Our national determined contribution. These main figures, and we take in consideration that very important for this point of view, the measure is the development of the nuclear option in our country. This chart was a study in frame of the International Atomic Energy Agency. You can see these charts, which provide the minimum emissions due to develop the nuclear option. So now let me explain you stressors impact on energy infrastructure of Armenia. First of all, we prepare this matrix or table. You can see in column our energy facilities is generation, TPP, MPP, and HPPs. Also renewables, small HPPs, lot in Armenia. Solar panels also in good developed. Wind is not so developed because we don't have a convenient sites for develop the wind farms, because its site is located on the high altitude, 1,006 to 2,000 meters. It's not so good for development of wind, and little bit biomass facilities. Next is transport. It's electric grids, which cover practically all territory of country. Gas pipelines, the main fuel which we can receive from neighbor countries is the Russia and from north and Iran from south. And oil products we receive by all pipelines. It can be in future if will be develop some projects. And railway. By railway we receive from other countries practically all necessary oil products like petrol, diesel oil, different kind of the freezing transformer oils, etc., etc. And very important point is the control. Control means SCADA. In this line, you can see the stressors which we analyze for Armenia and choosing for future studies. It's it's wind, like stressor, it's wind, temperature, some mud flows, landslides, lack of water, cloudiness, and lightning activity. In cross of this line and column, you can find this science which can be characterized the impact of the stressors. For example, for nuclear is the wind, atmospheric temperature, and lack of water. Let me say it's not some direct impact, and in future presentation I'm explain you the relations between different facilities, because that is all these facilities operating in union system, and between, for example, MPP and other facilities existing visual and invisual links. Anyway, my advice to you, before should be prepare such kind of the matrix, for example, for your country, and this matrix can be key for future studies and other kind of the actions. Now let's explain you some details. Thermal plants. Of course, we can take in consideration MPP also as a thermal plant. You can see there is a very bad impact of temperature. And when temperature increasing to 3 degrees, the efficiency of thermal plant can decrease to 1%. Also very dangerous for thermal plants, it's reducing water for cooling and for all the technologies which it's including in thermal plants. However, let me explain you for Armenia, we have a combined cycle gas fire plants, and this is not so danger for such kind of the facilities. More negative effect is the altitude of location, because we don't have a convenient sites for locating these plants, and 1,000 meter of altitude, 1,000 meter, decreasing efficiency even to 10%. Now let's come to the general matter of our presentation. It's nuclear option. At the moment, only one Rivier 440 second generation unit operating in our country. Let me explain. That is production of almost 40 production of electricity, almost 40% in generation balance of Armenia. That is unit cooling system of this unit, wet cooling tower, and need a lot of water, 30 tons per hour, and it is one main problem at the moment for operation of our nuclear power plant, because this is a huge volume of water, and we have some problems for provide so much water to the plant. Now, extreme weather and lack of water can be critical for equipment and processes for safe operation of our plant. Let me explain you some details of this issue. First of all, nuclear technology dissipation area is extremely limited. If you compare, for example, reactor with capacity 1,000 megawatt with thermal plant or thermal plant with boilers, about again 1,000 megawatt, this is area 10 times less than for steam boiler in thermal power plant. And if will be some problem in water balance, it can be very dangerous, even for reactor vessel, and can be provided some very dangerous situation. Point number 2. Point number 2 is the steam production by reactors. Nuclear technologies cannot provide a high pressure steam like in simple thermal power plants, 200, 300, or even 500 bars. It can provide only 44 bars after, of course, heat exchanger between and reactor and turbine. That's why this special turbine of low pressure operating in nuclear plants generally. And this, in this case, that need to provide a very low vacuum. The other case, droplets can stick the turbine blades. I was in low pressure section. I was in plant during the maintenance work and see the result of this phenomena. This is very, very dangerous for blades and turbine holes. And usually these blades in low pressure section changing, replacing during the each maintenance season of plant. About radioactive waste. Radioactive waste for last years, let me say, spent fuel is not qualified by an agency like a radioactive waste. And this spent fuel should be cooling before its special water pools during the 5, maybe 10 years. However, by Framatome, French company, we constructed on the site of the power plant the dry storage of spent fuel. It also need cooling, but cooling by air, by big fans. Very important, important installation in nuclear power plant, it's ventilation system. That can be provide some problem with radiation and nuclear PPP, and should be organized in case of climate change in right manner, right mode. Temperature can be very dangerous for sensors of measuring and control systems of the plant generally, and can be very dangerous for operation of nuclear power plant. Also, let me mention the backup diesel generation. It also need a very reliable cooling system, because can be some problem and backup diesel generators can even not starting. That is a problems which we looking in our nuclear power plant. I think in the same problems it's existing for many other nuclear power plants. Now, hydro. Hydro in Armenia, it's very important generation sources, because except production of electricity, they are provide following, let me say, system functions or services. It's load factoring that covered peaks. As I remember in Ukraine and the south of Ukraine was constructed nuclear power plant, and also the special water pumping plant for this issue. Hydropower plant is good facilities for voltage control in the grid. Also the function of frequency and interconnection flow control. Also in our case, it's the backup source for MPP. Also these deregulated water pools by this plant, the water pools, we can control water flow, especially for irrigation needs, because irrigation usually provide irrigation water provide by night time, and these water pools collected water and then in convenient time, in evening time, provide to irrigation system. Let me explain you scheme of the our hydro system, one of hydro system. We have a 2 cascade, so-called volatile cascade, 3 high pressure power plant, and 5 high pressure power plant located on the Razdan River, 5, 6, even 7 plants. We have a good opportunity provide additional water. Wait, I'm sorry. Provide additional fitting this natural water reservoir Lake 7 by special water tunnels. This is the one, it's called ARPA 7 tunnel. And this natural reservoir water can be provided enough water for irrigation and for energy needs. And about nuclear, this Argel HPP directly connected with nuclear power plant grid, and during the emergency situation, immediately can provide electricity for nuclear power plant installations, even much more quickly than diesel generators, 2 of them located in our nuclear power plant. Next, it's a small HPPs, both of them about 200 megawatts, capacity from few kilowatt, 10, 5, 10, even one of them 25 megawatts. This is located on the mountain, small minor mountain rivers. That is very inconvenient, because if no snow in the mountain, no water, and this is a private plants, and owner this small power plant losing his profit. That is one problem of this operation of these small HPPs. However, too much APPs in Armenia in results was a very created many problems for environment, because sometimes these owners using so-called sanitary water flow for electricity generation, etc., etc. Solar also on the good development of Armenia. but it's also very sensitive for climate change. First of all, it's cloudiness. It's clear, no sunshine, no electricity. And about the weather, it can be even destroyed these plants due to the effect of the windage or parusny effect in Russia. And lack of water, because these plants, if its sites located not so convenient place, can be dust or even ice covered these panels, and stop it is reduced efficiency, even can stop it operation. In this case, they need the water for washing of these panels. Wind farms, it's for industrial wind farms, the capacity 1, 2, even 5 megawatts. Operating speed usually 620 meters per second. But because it's my country don't have the good size for development of such kind of the farms, the sites located on the mountains, and then it's very changeable weather. And even in sometimes the speed of water come to the 50, 60, 70 meters per second. In these cases can be very dangerous for these facilities, damage blades and even towers of wind installations. And not too much bio PPP, I think only one installation, 0.5, maybe 1 megawatt. No, this is if it's not good weather, no food for this plant, no grass, no cattle biomass, and it's stop it for operation. Now let's come to transport. Like explained the previous presentations, that is very dangerous for overhead lines, especially for substations, the high speed winds, which can be damage or cross it the faces and come to the even system damages. Means created big accident situation for all power system. The temperature is also increasing the temperature. It's a very dangerous for substations because the influence on the quality of transformers oil, and then it's decreasing the efficiency of this transformer, and we increasing the losses in generally in the grid, because the main case of losses in grid, not in the overhead lines or cables, it's the losses in transformers. Also, let me explain you the special item when this increasing the temperature and influence of the oils, in transformer oil, which in transformer oil increasing the percentage concentration of the polychlorinated biphthalates. It's a very dangerous product. And when you, after a few years operating period, should charging the new oils in transformers, the using oil should be stored somewhere. And these PCBs, it's a very poison materials for environment. This is, let me say, additional effect of additional negative effect of temperature. Lighting. You can see on the map this zone of lighting activities. If we take a map of CIS countries, generally, you can see the small part of Armenia and Georgia, these mountains, Caucasian mountains. They are very active zone, about more than 600 lightings per year. That's why we are keep the special attention for protection our grids, our facilities, overhead lines, transformer stations, plants, etc., protected of lighting. In case of the bad protection, it can create a lot of negative processes for wholesale system. It's clear for any electrical engineer which is working in grid or in grids or in plants. What is? What was this? I don't see this. Sorry. Pipelines. Of course, pipelines is very important for Armenia, especially gas pipelines, because, as I mentioned, the main energy carrier, gas, provided from neighbor countries. And these pipelines crossing the mountains, all passes through canyons, and then it can be very bad risk from mud flows, landslides, and even floods, which can trigger the heavy rainfall caused by extreme temperatures, etc. That's why we have a special services in let me say, gas company, which keep a control for such kind of the phenomena. So next, pipelines. Very important route for energy supply in Armenia, like I mentioned, the oil products imported by railway. And these railway routes also located in very danger places. Again, crossing that mountain or hills, existing few special tunnels, etc. And also it need a special control for these railways and special forces for preventing such kind of the accident. Oh, something happened. Wait a minute. Also very important, this SCADA system. The modern SCADA system is based on optical fibers. It's located on the wires's and overhead lines. And lighting activities and wind can be very dangerous impact for these installations. And that should be we should be keep big attention for such kind of the impacts. Anyway, one of our proposals using so-called WAMS, Wild Area Monitoring System, which don't need such kind of the optical fibers, etc. That's using the satellite communication and can be using for monitoring and control of the system wholesale. That is a new installations, and now a lot of such kind of the installations located in Europe, few of them in Russia, as I know, and all countries, specialists of control and monitoring of all countries now keep this idea for implementation, these ones, very reliable, very quickly operating systems. Okay, thank you for your attention and welcome for questions. It's my city is Bible Mountain, Ararat, which I can looking through my windows every morning if it will be good weather. Thank you again.
Okay, Ruben, thank you. And for the very beautiful picture in the end, we will hope that this snow will never melt according to the climate change. And thank you for great examples of the not the adaptations, but the influence, of the nature and of the climate change to different systems. We will discuss it maybe in the end also. And now I have to pass the word to the next speaker, Dr. David Gernat, Netherlands Environmental Assessment Agency. The topic is climate change impact on renewable energy supply. David, are you with us? Yeah, I see you now. Hello.
Hello. Let me share my screen. Can I do that?
Yes, you can.
While the previous speaker needs to close the screen, I think.
Yeah, it seems to be. Can you?
I cannot
Yeah, I got it.
surpass it. It says
Wait
you
a
cannot
minute. Ruben?
start screen share.
Yeah, Ruben, can you stop the screen share to pass the word?
Yes, yeah, I tried to do it.
Okay.
I'm not so.
Mm-hmm.
I'm not sure. It's okay now?
No. I can still see your screen.
Wait a minute.
Yeah, sounds good.
Шановні колеги, зараз спікер буде розповідати про вплив енергопостачання з відновлюваних джерел. Так. Yeah, we are listening to you. Thanks, David.
Yeah, okay. So my talk is about climate impacts on renewable energy. My name is David and I'm from the PBL and Netherlands Environmental Assessment Agency. And we just published a paper called Climate Change Impacts on Renewable Energy Supply in Nature Climate Change. And I'm happy to share the results with you here. The story of the paper is that currently we are using 15% of global primary energy from renewable sources, mostly biomass, a little bit of hydropower, some solar and wind. But we all know that the potentials for renewables are very large, right? Solar more than 20 times, wind more than 5, 6, 7 times, even hydropower is really big. So in the future, we expect a lot more of those renewables. So some of the baseline scenarios show 20 to 30% renewables in 2050. 2-degree scenarios go even up to 50%, and some scenarios in the literature show even 100% renewables possible, right? Theoretically possible. So if renewables are increasing our energy supply, and we know that climate patterns fuel the renewables, so wind speeds provide the primary energy source for wind power, and also for solar and wind. Now, and we also know that these patterns are changing because of climate change. So maybe if we go into the future, our future energy supply will be at risk if we consider this climate change impact. So this is what we try to answer. So these 2 questions: how does climate change affect global renewable energy potential? And then how does this change in potential change the energy supply? So, and this is the conceptual model that we used. So here we have a price of a certain technology. This price produces a certain market share, with the lowest price having the largest market share. Then you have a certain use, and then you have 2 feedback loops. One is a negative feedback loop that lowers the price because of learning, and the other one is a positive feedback loop that increases the price because of depletion. So you have a learning curve and a depletion curve. Now, so what we are going to do here is change the supply curve so that we can include climate impacts. So how we normally do it, and so this is the example for solar. So we have a global map of solar. Then we calculate per cell what the potential is per cell. Then we also know per cell what the cost is. Then we make a cost supply curve, and we enter that in the model, and we combine it with a baseline scenario. Now, what we're going to do here is that, so we have the historical solar data, but using climate models, we also have future data about solar irradiance, and also for wind, and also for bioenergy, and also for rainfall. So then we can calculate the difference between a climate change scenario, like a baseline, and then we can compare it with the historical ones. Now, and then we know the difference in potentials. Then we have a shift in the cost supply curves, and then we also have a shift in the energy supply. Now, we did that for 8 technologies. So for utility scale PV, rooftop PV, concentrated solar power, onshore wind, offshore wind, bioenergy first generation, bioenergy second generation, and hydropower. And then we used 4 global circulation models from the IPCC AR6 5 database, 2 scenarios, one baseline scenario that goes up to about 3 or 4 degrees warming, and one scenario that goes to 2 degrees warming. And from those climate models, we collected irradiance, temperature, wind speeds, yields, and runoff. Now, the overall formula is to calculate climate impacts is actually very simple. So it's, yeah, so overall, if you have more wind or less wind, then you have more wind power or less. And that applies for solar, for wind, for hydropower. Yeah, but you have a few effects that are counterintuitive. So PV, for example, if you have a higher temperature, then the conversion efficiency of the panel goes down. But for concentrated solar power, a higher temperature increases the efficiency because you have less losses to the environment. For wind, you have a power curve, and also for hydropower. So for those interested, so this is the power curve for a wind turbine. You have a certain cut in speed and then a certain cut out speed. And if the wind speeds are higher than this, then the windmill is switched off. So and for hydropower, you have this flow duration curves with a certain amount used, this blue area, but also a certain amount of water spilled. So the dynamics of climate impacts are in these conceptual frameworks, and that changes the results. But in general, yeah, if you have more wind, more wind power. If you have more rainfall, more hydropower. Now, so we collected this data, and so this is irradiance, this is temperature, this is, I believe, first generation yields for maize and sugar. These are second generation bioenergy, so this is mostly woody bioenergy yields. These are wind speeds, and these are this is rainfall runoff. Now, we have the data for the historical situation. Then we have it also for the future. So for the 2100 period in an RCP 6.0, that is a baseline that goes up to 3 to 4 degrees. Now, and then we know the difference for each input parameter. So this is temperature. So temperature goes up. This is irradiance. That is very scattered. The dots signify so if it has a dot, it is significantly different from the historical situation. If it doesn't have a dot, then there is a high uncertainty in that cell. And so for temperature, you have dots everywhere, so that seems to be quite certain. For irradiance, you have dots only in certain places. So this is wind speeds. Dots in about half the places. This is rainfall. In the northern areas, it is quite. It seems to be quite certain, but in the rest of the world, not. So this data will have effect downstream. So if we go downstream, if we go to the energy model, this is the original input data that goes in it. Now here. For biomass, it's there's an interesting story here. So this is first generation biomass, maize and sugar, and this is woody. Now there is a big difference if you consider CO2 fertilization or not. So CO2 fertilization is the effect that when you increase the CO2 concentration, then you have higher yields of plants. So plants grow better with higher CO2 concentrations. So we know this is true because they also, we inject CO2, for example, in greenhouses to increase plant growth. Now, and that same effect also seems to be the case globally. But what is uncertain is the strength. So the strength of the effect. So what we did here is we have a scenario with CO2 CO2 fertilization and a scenario without. And then we can assess the strength of the effect. Now, then if we have this difference in primary input data, then we can calculate the change in technical potential for all the technologies that we consider. So PV, CSP, wind, hydro, and bioenergy. Using that technical potential, we can then make this graph. This is the so if you add all the cells up and you plot it in a bar graph, you get this picture. So on the left side is the absolute difference in terms of exajoules. On the right side, you have the relative difference in percentages. Now, if we start with the green bars here, and so you see that bioenergy potential increases up to 20 to 40%, both first generation bioenergy and second generation. So that is a big difference. So also you see it in absolute numbers. Also, second generation bioenergy increases up to 40 exajoules. Now, if you don't consider the CO2 fertilization effect here, then you get this red area here. So the positive effect goes away if you don't include CO2 fertilization. Now, for the other technologies, you actually see only a very minor difference. And so here are the solar technologies, utility scale PV, rooftop PV, and concentrated solar power, hardly any difference. Now, for wind, it seems to be, I mean, it's still minor, but seems to be leaning towards the negative. And for hydropower, it seems to be leading to the positive globally. Yeah. So for this can change per region. So now we are going to use that information and put it in our energy model. So we are using the image model, and with that model we implemented the SSP2 RCP 6.0 baseline scenario. Very technical term, but it is a baseline that is generally used a lot in the literature. The middle of the road scenario that kind of it takes the trends that we have seen in the last 50 years and then kind of extrapolates that into the future, and that leads to about 4 degrees warming. Now, here you see the primary energy. So this is a population, this is GDP, this is final energy, and this is primary energy. So we are now here, oil, coal, gas, and a little bit of renewables. Now, if we go to 2050 and 2100, you'll see that fossil fuels grow a lot, but also renewables a bit, but they are still in the minority, let's say. Now, in the other one is the 2 degree scenario, and there you see that the fossil fuels disappear and get overtaken by the renewables. Now, so again, this conceptual model. So what we are now changing is this cost supply curve. So we are changing the cost supply curves in order to simulate the climate impacts that I showed you in a few slides before. Now, and if you do that, then you get this result. So this is the change in primary energy in 2100 compared to a scenario without climate impacts. And so we ran 2 scenarios, one with climate impacts and one without. And then we checked what the difference was in 2100 between those scenarios. Now, if it is blue, then you have an increase. Then climate change causes an increase in the primary fuel supply in that region. And so this is the bioenergy column, and these are all the regions that we see here. So here's Ukraine. Keep your eye on this one. But you see that for most areas in the world, you see a positive effect because of climate change on bioenergy. Now, and this is the scenario with CO2 fertilization. This column here is the scenario for bioenergy without CO2 fertilization. So it is mostly blue here, and it has these dots also, so that means it's statistically significant from the scenario without climate impact. So it's quite certain and quite blue, but that disappears in the scenario without CO2 fertilization. Now, the other ones, hydropower, wind, and solar, have a very different look, right? So they are far less certain. So they have far fewer dots. They are also red and blue. So red means a decline. And if you look here, this is the indication of the uncertainty in the data. So if it is dark brown, then you have a very large absolute standard deviation compared to the mean. Hydropower has some regions where it really increases. So here you have more rainfall, basically, but you also have some regions that are declining in hydropower. So here you have Mexico and Korea, and Central Europe also a bit, and here a few regions. Now, do note that these regions don't have dots in there and are not statistically significant. Now, for wind, actually the same story. Blue and red, here and there a dot, but not a lot. The impact on solar are actually, also minor. It's a bit more certain, but not a lot. Now, and then here is the other column, and other is all the fossil fuels plus nuclear, and you see that this column is mostly red, and that is because bioenergy replaces fossil fuels. So because of the increase in bioenergy, we have a decrease in fossil fuels and nuclear. So, but overall, because of climate impact, you have 4 to 7% more renewables in your system globally. Now, if you look at Ukraine, the effects are minor as far as we can see, but this graph doesn't tell us a lot. So I looked a bit deeper in our Ukraine scenario. So this is the baseline SSP2 scenario of Ukraine. So this is the IEA statistic data, and this part is our data to show you that we kind of we're modeling Ukraine quite well, and then we have a slow increase in primary energy supply up to 2050, and it's mostly dominated by coal, oil, and gas. And so this research here is dealing with this part. So it has a little bit of solar and a little bit of biofuels and a little bit of hydro. Now, if we then look at the first table, here you have a table showing the change in potential in Ukraine per renewable energy technology. So here you see again, So here you see again the increase in bioenergy. So this is the different climate models, and you see almost like 100 to 150% increase in bioenergy potential. For hydropower, it's mixed. So 3 models show an increase, 1 model a decrease, an average of 8% increase of hydropower potential. Solar, kind of the same story, a modest increase, 10%. For wind, it is really mixed. So you have 2 models that show modest increase and 2 other models that show a strong decrease. Now, if you put this information in an energy model, then you get this result. So remember, it is only about this little part here. Now, and then you see, as expected, that you have a little bit more bioenergy, a little bit more hydropower. Apparently, you have less wind and less the rest. That's the fossil fuel and nuclear. So some of the increase in bioenergy and hydropower causes wind to decrease, and nuclear and hydropower also. Now, wind can also be a direct result of this large decreases here. So, so to conclude, I mean, it's generally this research shows good news. I mean, no serious negative impacts as far as we can see, and possibly some positive. So on bioenergy and in some regions hydropower. Bioenergy also applies for the Ukraine. I mean, it does depend a lot on this CO2 fertilization assumption. I mean, the strength of it is uncertain, the effect not. Now, in hydropower and wind show mixed results, and impacts on solar are really minor. Now, I have a few slides here after to show you the 2-degree scenario and some formulas and literature, but I will send this presentation to you that you can look it up yourself. Thank you very much. This was it.
Yeah, thank you, David. Actually, a lot of information, and I'm still making some notes about your presentation. Please send us these precious materials, because yeah, it's very interesting when the situation changes, when you take different type of scenarios, and one of them shows decrease and 3 are showing increase in productivity or something like. So which one to believe? And we have, and we have the new technologies to arise during these 80 years. So maybe the situation will be changed by the new technologies or new materials or something like that.
Yeah. So that is a very important point. So so this research assumes current technology. But you can imagine that in the future you have new technology that can deal with the climate impacts. So some of the effects that we now calculate can be less or more depending on our learning process.
Yeah, that's right. Yeah. But actually, it's very interesting, and we are doing also some investigations and some modeling scenarios right now for Ukraine and for maybe more precise districts. So it's very interesting for us to plunge deeply in this investigation. Okay, thank you, David, very much. Yeah, and stay with us if you can, if it's possible. Okay. And the next speaker is Sofia Simuel, using climate data for the operation of power plants. Sofia, are you here?
Yes. Hello, good afternoon.
Hello.
Thank you so much for inviting me to be here. I'm not sure exactly how long do I have to speak?
Well, you don't have limitations right now.
Okay,
so
wow. You should never tell that to a researcher.
Yeah, I know, but actually the situation is like that because a lot of scientific people right now here, and we cannot limit them to have enjoy with your speech and with your presentation.
Okay, so then I would like to share my screen. I will try to be concise, and if you just interrupt me if I take too long.
Okay, sure.
I'm trying to put, I hope everything is working from your side. Can you see my screen well?
Yes, we can see your screen and we see the first slide. Everything's okay. Mm-hmm.
Okay, so thanks again for inviting me. I'm a researcher at the Portuguese laboratories in the energy transition and energy resources. And I've been coordinating for 3 years a project looking into climate variables and how they affect the European power sector, the whole of Europe. We did not include Ukraine, I'm sorry to say. So what we are trying to do, what we have done in this project, is to take this huge amount of data, similarly to what the previous speaker said, and integrate it into an electricity model for the whole of Europe. And why is this important when we are talking about electricity models or energy models? Is because the models that the European Commission and lots of researchers and policymakers are using at the moment, they do not consider future climate. So my point is, we are trying to develop policies, you know, greenhouse gas mitigation and targets to reduce emissions and to change the power sector as well as other sectors. But in most cases, so far, sorry about that, we assume that the wind and the hydropower and the solar PV is going to work as it has been working in the past, because it is very difficult to include in detail into the models that exist already different variations of climate. And this is just an example from a communication from the European Commission in September, where they show how the European power sector will become carbon neutral without liquid emissions in 2050. And I do know that the model they have used, which is PRIMES, did not consider future climate conditions for the operation of the power sector. And very important here, because of when we talk about adaptation, a lot of times we are talking about extreme events, you know, storms, snowstorms, windstorms, droughts. But here in my talk, I'm going to talk, like I think the previous speaker talked about, the change in average precipitation, average wind conditions, average solar conditions. So extremes are even more important, and they can very, very much affect not only the power sector, but I think everything we do, extreme events, but we are not so good at modeling them. So I'm just talking about changes on average climate conditions. So what have we done in this Clean to Power, this project? We took climate data, which is the ball that you see there on the right-hand side, and we translate that climate data into changes in hydropower, solar PV, and wind power plants availability, the number of hours they can operate in each country. In Europe, temperature can have in changes on the demand for electricity for space heating. We didn't have time to look into space cooling because we will need more cooling. How this could affect the operation of power plants. And we also did a small analysis on what could this mean if we consider the increased amount of water used for agriculture. But we did this only for Iberia Peninsula, and I'm not going to talk about it now. So then we took all these different bits that climate can affect the power system, and we put it in the ball in the middle, which is a power system model, a model for the whole of Europe. And some of the things we measured in terms of indicators, things that are going to affect the power sector, have to do with the different changes in the amounts of electricity you need to store just because of changes in climate. You can if you consider future climate, does it make a big difference in prices of electricity? Would this affect the operation, the dispatch of the power model if you have different climate conditions? What would this mean for CO2 emissions? I mean, Europe and lots of countries have their greenhouse gas emission reduction targets for the power sector. If the wind, the sun, and the precipitation change in the future, will that create a risk for complying with our emission mitigation targets? And then we look at other things like the costs for operation and maintenance and implications for acquiring and storing fossil fuels. So a lot of work. And it was also a lot of work, and this is a complicated pictures just to show you, as I think you probably know how difficult it is to take a huge amount of climate data, and the previous speaker talked about it, that in fact you have different climate projections that tell us different things, and if you want to be rigorous, you have to consider them all. So in this project, it's a huge amount of data, and one of the big challenges was to make climate models talk to energy models. These are different scientific communities, we speak different languages, and it is a big challenge to get all the data organized in a proper way to work with different models and different tools. So we started on your left-hand side with the climate data. In this project, we worked with two different timescales. We work with seasonal forecast term climate projections. Seasonal forecasts is going to just talk about long-term climate projections, and for us this is mid-century 2050 and also 2030, but it's very important for Europe. These are 2 years that are very important for policy making in Europe. So that's Eurocordex climate projections. And this is not one climate projection, it's in fact 11 climate models. And 22 future climate projections are equally statistical simulation tools for I think I was out of the connection, but I'm here again.
Yeah, it seems to me that not only me have this problem. Can you repeat please the last minute?
Okay.
Maybe it's the problem on your side. Yeah.
Okay. Did you catch it? Maybe on my connection? Can you hear me?
Yeah, I can hear you right now, Sofia.
Okay, so I'll just try again and let's see how the internet connection works. So I was basically saying that we need a lot of different methods and approaches to work with the amounts of climate data, and we have to translate temperature, wind speed, precipitation into amount of hours that the power plant can work. We use the combination of models and tools that goes from hydrological models, machine learning to statistical simulation. And then we took this, everyone is familiar with it, but basically a capacity factor is it measures, let's say, the percentage of the year that a power plant can work. It depends only on climate. So, and we put this into an energy model. And we have done this with a lot of different power companies and policymakers, the Environment Agency, to try to produce information that would be not too scientifically complex. Example, the carbon intensity of each generator watt-hour, these type of things. So a little bit of our difficulties and a little of our results. For every year was also saying that they're all sentient when we talk about future climate, and here
I'm sorry, I think that we cannot hear you, Sofia. We see you right now, but we don't hear you.
Yeah, you know, I think now you can hear me. I think this is really my internet connection. If this happens again, I don't know, maybe we postpone my talk, I don't know. Can you hear me now?
Yes, let's try once more about this slide and
Okay.
yeah, for different 11 different climate models. Yeah.
Yeah, so basically this is, I think it builds on what you were saying before, that if you look at the different ways climate is going to affect Europe, on the left you have historic, on the right you have the future. If you see more red, it means dry, less rain, and if you see more blue, it means it's going to rain more precipitation. And as you can see, it really changes from climate model to climate model and for our different climate change scenarios. And this is a challenge to work with all this information. Another challenge is that when we talk about future climate, it's not enough to work at national level, especially Ukraine, which is a very large country. We have to look into the different climate conditions in each country, and we have tried to do this. You see there a map of Europe divided in different little regions that we try to have, you know, wind speed for each one of these little parts of Europe. What happened was not very nice, because once we tried to use this huge amount of information, our energy model was not running. Basically, it became too big to compute. There is, of course, a way to solve this, but it takes a lot of time and resources. And now you can see one of the in capacity factors. This is an example for Portugal. We have this for other countries in Europe.
Sophia, I'm sorry to interrupt you, but there is advice from our audience that you could try to turn off the video, because it takes a lot of internet connection.
Okay.
Maybe that would be easier. Yeah. Let's try now. Yeah, let's try.
Okay, so these 4 charts you can see there. The left upper one is for solar PV. Below you have wind onshore. On the right upper corner you have hydropower, and below that you have wind offshore. And what we are showing there is how the change in the capacity factor could happen in the future if you consider climate change. So what you see, I will just focus on solar. What you see is for a spring day, a summer day, a fall day, and a winter day, the dotted line represents the historic operation of the solar power plant. And of course, it generates more power at lunchtime. This is normal, we have more sun. And then you see a pink area. The pink area represents what we think is going to be the change in the capacity factor with climate change. And of course, in summer, we see an 8% increase in the operation of the power plant. And for other countries and other times of the year, we see that it can operate more hours. So that the solar profile is going to change. For wind onshore, you can see that it really changes with the scenario, so below the solar PV. And we can see, for example, that for Portugal in winter time, you can have actually less operation of wind power plants, or a little bit more, depending on the climate change projection that you're looking at. This is more or less the same trends you can also see for offshore wind power. And for hydropower, I would like to say that it varies so much that we cannot really say what could happen with hydropower operation, in this case for Portugal, although we think it's going to be generically less hydropower, less water availability to generate power. So we include them into an energy optimization model for the whole of Europe with all the different countries. And basically what we want to see with this model that we run until 2050 is what happens if Europe wants to be a carbon neutral power sector, so we don't want to have emissions, greenhouse gas emissions from our power sector. It means that we will not have coal anymore in 2050. But what if we do but now we look at all countries in Europe at the same time? And what happens to all countries in Europe at the same time if the climate is changing for the different countries and they are, you know, connected and selling electricity to each other? Would this actually make a difference in the results? That's what the type of things we were trying to look at. So this is one example of some of the results we see. It's a complicated chart again, so I tried to explain it. This is below, you have each country in Europe. On your left-hand side, you have the percentage of electricity that is generated for renewable power in Europe. And what you see, the gray bars represent the percentage of renewable electricity for each country in Europe now, as we know, as of today. So the European average for the whole of Europe is around 30% renewable power. And can you hear me?
Yes, we can.
Yes, we can hear you well now.
Very challenging. Okay, thank you. So the big bars represent the percentage of renewable electricity generated in each country at the moment. For Europe is around 30%. And the green, the dark green and the light green bars represent how this percentage can change if you consider future climate conditions. And because it's not one future climate, we don't really know how it's going to be. You can see that for some countries, the light green bars and the dark green bars are very wide. So it means that the percentage of electricity generated from renewable power for these countries can vary a lot depending on which type of climate we have in the future, with the knowledge we have at the moment. Whereas for other countries, they are not really very sensitive to climate, to future climate conditions. So to give you an example, you see Romania here on the right-hand side, where currently Romania has, let's say, around 42% of electricity generated from renewable power. By 2030, this is the light green bar, Romania can have, depending on how the climate is going to be in the future, it can be either for 38% or 45% renewable electricity, or it could be more than 60%. And this is just because of the climate. So that's how important it is to change what the cheapest way to produce electricity in the future if you consider different climate conditions. By 2050, the percentage of electricity generated from power from renewables increases because we are, again, as I said before, we are taking Europe towards carbon neutrality. But for the case of Romania, for example, how much it increases, it can be below 70% electricity from renewables up to 90%, depending on how wind and solar and hydropower future climate conditions are going to be. So Romania is one of the countries we have found is very sensitive to future climate conditions. Other countries less sensitive are, for example, Lithuania. Okay. You can have, I invite you all, if you want, you can go to this website that we have prepared in this project. You will see a figure like the one I'm showing now. If you go to the detailed map view, you can have access to an interactive tool where you can, let's say, play around with the results and see different results with different indicators for different countries in the European Union. This is an example of the results you can see. This is again an example for Romania. What you're looking at is a total of electricity generated from hydropower in Romania for a spring day in 2017, so that's, let's call it now, and you can see that the hydropower profile in Romania in 2017, it increases during the night. There is a slow decrease around lunchtime, and it then increases again and it goes down. This is of course a response to the demand for power. So that's the left upper the slide. This is the amount of power generated from hydropower now, so it's, let's say, historic values. You have on the right hand side the amount of hydropower generated from Romania if you consider the seasonal forecasts for last year, so let's not go into that. And below you can see a representative spring day for Romania in 2030 and in 2050 if we consider future climate conditions. And there you can see there is a big lots of blue colors, and the blue colors represent the different amounts of hydropower that are generated if you consider different climate projections. If you go into this web service, you can change and you can see electricity generated from hydropower or for wind or from solar. And what you will also see is that whereas, for example, hydropower, there is a big dispersion in results, lots of different codes of blue. For example, for solar, climate change, the way we have worked with it, doesn't make a big difference in the amount of electricity generated from solar, whereas hydropower and wind power are much more sensitive. These were some of the things we've been working with in the Clean to Power project. Again, it's not extreme events. It's just average conditions. And also, I think it's very important to highlight, and I think this is also quite relevant for Ukraine, I think, that one of the ways to deal with climate change in average conditions is to be able to trade electricity across different countries, because it could be that you have, at the same moment that you have less wind, that you have a wind drought, if I might call it like that, there is another country that is having a lot of electricity generated from solar, and you want to trade that electricity. So in our point of view, an adaptation strategy to deal with climate change is actually to be capable to trade faster and more effectively across lots of different countries. Another key message I would like to share with you is that, again, this is a very difficult topic to work with because of the huge amount of data we are talking about, and because we are putting two different communities together, in our case, climate scientists and energy modelers. So there's a lot of things we have to learn how to talk to each other. And also it is quite tricky to communicate these topics. As you have seen, I mean, we try to make our slides and our charts as easy as possible, but they are pretty dense. There's a lot of information. So it's very challenging to communicate this to decision makers, to power companies, and to policymakers. Finally, we have found that for the whole of Europe, in total terms, for the whole of Europe, we can comply with climate change in average terms. But this means that for different countries, it is very challenging, and for others, not so much. So it is very, very important to look at country level and even at regional level within a country to really have a good picture. And that's it from my side. And sorry about the bad internet connection. Thank you very much.
Okay, Sofia, actually, thank you very much for this wide framework that you showed in your investigation, and this understanding, I mean, wide understanding of real sustainability for whole the Europe. What should we do with all these models, and how can we cope with not understanding the future climate for definite, maybe at the moment, so we can cope with this situation anyhow, just with collaborating and communicating and finding other ways to solve these difficulties in adaptation. Thank you very much. Okay, and the next speaker Oh, Yefrad, it seems to me that it's your turn now, and the stage is yours.
Okay, can you just make sure that I can share my screen?
Yeah, let's try.
Okay. So before I start, we had such a broad set of sessions today. So I would just like to just summarize very briefly some of the issues that have been discussed. You know, the climate change parameters and how they change, how we look at the system, the changes to the load calculations and the system, the changes to the energy mix, as well as, and I'll be talking about some of the technical changes to assets and behaviors, just to give you a range of some of the issues that we are facing. So, okay, it's not coming up. So, okay, there we go. So I want to give a couple of examples of structural adaptations, that are needed at the technical level, as well as some behavioral aspects. And then if we have time and you're interested, I can give you an example of climate risk and vulnerability assessment that was done for the power system in California, if we have time and you're interested. So as was mentioned, hydropower is critical. It remains a very critical part of the energy mix in general, and especially in Europe. One of the things I think we need to be looking at when we're looking at climate change is understanding how the different climate drivers change how we're looking at the design of facilities, right? So obviously precipitation and river levels are already being considered as part of hydropower, but now we also need to look at frequency of extreme events, changes to snowmelt, changes to glacier, decreasing river flows, increasing temperatures, all of which change different aspects of a system, right? I also want to mention, even though hydropower is considered renewable energy, it actually is quite intensive from a GHG emission consideration, both at the carbon level and for methane, which is not typically considered for hydropower, and definitely not considered as part of GHG counting, or at least the methane isn't. The carbon might be, but the average is 100 grams of carbon and 100 grams of methane, more or less, for every kilowatt that you produce. So if you have a lot of hydropower, you are producing, it's not a fully renewable source, or not 100% zero source, I should say. Adaptation options are actually quite wide, and these are very technical in terms of their focus. So we're looking at risk-based engineering and planning, which I hope all plans were designed with already. A better understanding of the cascading impacts of what happens when you have a series of plants on a river, or when you have reservoirs and plants, as well as cities, and how they link together. Changing the operational regimes of reservoirs so that they're better adapted to new climate conditions, climate proofing of engineering interventions, making sure, for example, that your that your switches don't get flooded, right? Because if the switches are protected, the system can work, or similar things like that. Changes to dam construction, changes to dike construction. Changement to the management of spillways, component-based flood barriers, integrated water management, and improved watershed management, I think, is a very underestimated aspect of flood management and hydropower management, expansion of flood capacity, of plant capacity, management of reservoir capacity, installation of monitoring systems on rivers so that you can better adjust your operational procedures, better forecasts, of course, relocation of plants and sometimes communities, which is something they've been doing quite a lot in China mainly, but not just. All of this requires high resolution climatic and hydrometeorological scenarios. So your energy sector people need not only to be able to develop this capacity to do some of these calculations on their own, but they need to be supported with very strong capacity at the hydromet level, at the national level, but also at the regional level. And then I want to talk about specifically, well, I'm not going to talk about it. I will show you a little video, if you allow me. EDF, which is Electricité de France, has developed an adaptation to expand the capacity of hydropower plants. They call it the piano key weir system. So if you give me a second, I will bring up the video. It's about 2 minutes, so it shouldn't take too long.
Okay, don't worry. Yeah.
Okay, so I'm sorry for the French. Basically, this system allowed EDF to expand the capacity of 10 or 15 plants in France and about 20 plants in Africa by 20% each, just by adding those crenellations, what they're calling the piano keys. It doesn't work on all systems, obviously. They're obviously trying to sell this, but my point is that even with existing systems, there are some technical and structural solutions that can be developed when you start looking at things a bit differently without rebuilding plants entirely or totally decommissioning them. So, okay, let me see if I can bring this up again. Nope, it doesn't want to come up. Sorry. Okay, sorry. This is a little technical difficulty here for some reason. Okay, let's see if I can get this going now. Apologies, this is
Take your time,
stuff.
It's okay, yeah.
Yeah, I think we had some really good presentations today. Okay, the other part I wanted to talk about is transmission networks. There was quite a few mentions of transmission networks. And one of the things I think that we tend to underestimate with transmission networks is obviously how important they are. There are quite a few mechanisms to or options to improve the capacity of transmission networks. Obviously, you have the simple things like trimming trees at the local lines. underground cabling, which helps if you do it correctly with flooding. It helps with some line sagging. It obviously has heat-related issues, as Ruben mentioned. Installing power lines, implementing the low sag conductors, which I'll talk about a bit more, smartening the network, improving switches, so facilities and conductors better work under different conditions, changing the distances between lines, which changes also costs and things like that. Micro generation and renewable energy sources is something I think that a lot of grids are looking at. And then, of course, you have the ultimate one, which is lightening the load. And for those of you who say, well, lightening the load and energy efficiency is mitigation, you're absolutely correct, but it is also adaptation. So just a simple example, at least in the US, they use the ACSR cables for the transmission lines, for the high voltage lines. And they can lose, depending on how old the system is, up to 20% of electricity on those lines. The US grid is very old and has quite a lot of losses. They have started in the last 10 to 15 years to transition to, they call it reconductoring, and they're trying to use these ACCC cables. So first of all, they're lighter, so that they can have longer spans, so you don't need as many struts, right? And poles to hold the system up. They're lighter, so they don't sag as much on hot days. So especially in the south of the US, where temperatures can go up to above 45 degrees easily on a consecutive 2-3 week period. You can have that in Florida and Georgia and Mississippi. You have that on a regular basis. So reducing the local sag of the pole lines has been transmission. They are saying that it's also saving them money. I'm not quite sure on the details of that, but at least the preliminary data that's coming up from the first 10 years shows that it's also saving about 5% a year in terms of maintenance cost. So this is just one of the options. It doesn't require redoing the system. It doesn't require rebuilding, but it's still an adaptation, a very simple technical adaptation that should also be considered among all the other adaptations that we're looking at, the energy mix, efficiencies, and improving the overall capacity of the system. Of course, distributed energies generation units, which I'm not an expert in energy. Please don't expect me to talk about this in much detail. But distributed energy generation units are very popular and are becoming much more popular as ways to support grids, not only to reduce failure points, but also to improve the energy mix of the grid itself. So I want to talk about a program that, my computer is stuck. Oh, there we go. Okay, so in response to Hurricane Sandy, New York State, not New York City, this is the state, developed what they call Reforming the Energy Vision, REV. This is basically they have through a program to redo the energy grid for New York, because the U.S. the U.S. actually has six energy grids, right, that are regional, and then in addition to that, each state has its own policies for each grid. So New York is part of the Northeast grid, but it is part of 10 other states that make up that system. Anyway, for New York specifically, just for the New York part of the grid, they want to have by 2030, 50% energy generation from renewables, 90% reduction in GHG from 1990 levels, and 23% decrease in energy consumption from 2012 levels. The key problem that they're facing is they needed to change the business model for the energy companies, for the utilities who are providing electricity, because today the companies, like in most countries in the world, they're charging you per how many kilowatts you use, right? Your energy consumption is what you're paying for. So they developed a very complicated program called Value of Distributed Energy Resources. It's a what everybody affectionately calls a VDER tariff. And basically, instead of net metering, which is basically a kilowatt for kilowatt exchange, this has a very complicated process where you're producing, it goes into a general pool, and then the electricity utilities pull from it, and they update the system every 15 minutes, and then they pay you accordingly. So this has actually been incredibly successful, surprisingly enough. In 2000, for example, in 2018, there were 100 megawatts of distributed energy solar projects in New York State. In 2 years that this has been operating, there are now more than 1,000 megawatts. So that's a 10-fold increase in the number of distributed generation storage projects. In addition to that, independent systems. So independent systems is what residential or small solar energy projects would fall. So if I put a solar panels on my house, I would be considered an independent operator, right? Because I can sell to the grid. So the number of megawatts produced through small independent systems or small independent operators has jumped from 1,400 megawatts to 8,000. So in a space of 2 years, New York State has managed to transition 9,000 or generate an additional 9,000 megawatts into the system just based on this tariff, which is incredibly popular and has been very successful as an incentive, not only for people to produce more energy storage capacity, both batteries and distributed generation, but also to make the grid itself more resilient, because you're changing the mix of energy that supplies the grid itself. So I just wanted to bring this up as an option, that this is also considered an adaptation option. We tend to think of tariffs as reforms and policy, but policy reforms could be considered adaptations as well. And then lastly, I want to speak a bit about customer incentives. As I said, the US, speaking specifically for the US, the grid in the US is made out of multiple small grids. So you actually have a lot of testing that occurs at the smaller level, at a localized level for changes. But some of the things that you see quite a lot is flood protection measures for making sure that the facilities don't get flooded, wind protection so poles don't fall down, drought protection so that thermoelectric cooling and utilizing of non-freshwater sources. There's apparently an expansion of an increase in low water use generation facilities, modernizing the systems entirely, some of the things Ruben talked about with SCADA systems and sensor and controls and smart network monitoring. And I'm not going to talk about preparedness because this is unique to the US. And then, of course, there's programs that have been put in place. So, for example, to address higher temperatures and more severe stormwater, Florida Power and Light offers incentives to switch off home uses at certain times. Entera, which is in Georgia, has added capacity. So you have both customer incentives as well as operation change that incentivizes changes in behavior. In places where you're looking at decreased water availability, you have there's been a lot of technological changes, putting in new facilities that are using modernized technology, as well as starting to use climate risk and vulnerability assessments a lot more in planning the network. Where we see a lot of wildfires, mainly California, you're seeing a lot of operational changes in how the system is being maintained, when trees are being trimmed, when lines are being straightened, when transmissions and substations, are being checked, And where we have sea level rise and more intense hurricanes, you're seeing a lot of technology changes. Not mentioned here is what Florida is doing for rising seas and more intense hurricanes, which is basically putting walls around all critical facilities so that you don't get damaged. So for example, the nuclear power plant in Turkey Point, south of Miami, is they're building a 18 foot is 9 meters. So they're putting a 20-meter wall in front of the power plant to prevent the waves from inundating the nuclear power plant. They're building a series of walls that literally are going to stop the waves, which is crazy. Okay, and now I want, and in addition to this, I want to talk about a very unique program that has been incredibly successful in the US. It is so this started in this is a company called O-Power, and they started in 2008. They're now operating, I think, in about 50% of the electrical utilities in the US, and they used basically behavioral policies, behavioral psychology, I should say, or what is called green nudges, to convince people to reduce energy use. And they did that in two ways. So the first thing is, every time you would get your bill, they worked very closely with the energy company. Basically, they were paid by the energy companies. So every day you would get your bill, they would hang on your door. They would have a delivery that would hang on your door, these little flyers like you have in a hotel, you know, like the piece that says for the hotel, don't, you know, I need room service, or I don't disturb me. And it would say, your neighbor is using 10% less electricity than you are because they are doing so-and-so, right? Or within 1 kilometer of your house, 60% of people have started to use LED light bulbs, things like that, right? And then in addition to that, in the bill itself, they would include recommendations to reduce your bill. This was based on a lot of very accurate data for energy usage. So your bill would include things like, you're using a lot of electricity between 10 and 12 in the morning. You could reduce your cost by 20% if you do so-and-so, right? So this was very specifically linking to two things. One is specific recommendations for changing behavior patterns. And the second is telling you what your neighbors are doing, because a lot of us don't know what our neighbors are doing, and basically creating popular pressure on people just by making them aware of what their neighbors were doing to save energy and to save money. So one of the results of this was actually quite substantial results, which is why it became so popular in the US to reduce energy efficiency. Overall, I should mention that the US has not had a new energy facility. No new plants have been built since 1970. And at the same time, there has been a reduction in per capita use of 20% since the 1970s. There's been a per capita reduction in energy use of electricity at home of 20%, which is incredible when you think of the amount of new electrical facilities and gigawatts and gadgets that we use now, computers and iPads and God knows what else, streaming, and we still manage to reduce the amount of energy. So I want to talk, going back to this. So you have two types of savings. For the company, you have fewer people, 10% reduction in changes of company of who provides your electricity, right? So that's a huge savings for the company. A 22% reduction in the cost of serving energy because of savings, because people are more efficient and starting to reduce the amount of energy use. And a 12% increase in customer satisfaction. So people are happier with a company because they're telling them how to save money and how to save energy. The other thing that you're seeing is a 60% increase in participation in energy efficiency programs, a 15% increase in requests for smart energy, smart meters, right, that are giving you much more accurate data to the system. and almost 5% increase, not 5%, five-fold increase in people who are opening up the awareness programs and awareness information that is being sent by the electricity companies. So what you're seeing is something very small, as simple as these door hangers that, as well as a little line in your bill that says you can change your behavior or you can save money by doing so-and-so, has created tremendous benefits to the electrical companies, not only in terms of customer service they're providing, but also in terms of the engagement with the customers and people's ability to engage with energy efficiency programs. So this program, this company has really changed a lot of the way that customer incentives are being done. And I think they are now part of Oracle. Oracle bought them out like within 4 years. But they really changed how people were starting to think of energy efficiency programs and providing customer incentives for changes at a household level. That's really the end of my presentation, unless you want me to talk a bit about the CRVA, because I just wanted to give some practical examples to the really good high-level examples that we have gotten from all the previous presenters.
Yeah, sure, Efrat. As for me, I would listen to you till the end of the day.
Oh no, you would go crazy.
Maybe so.
So, so do you want me to talk about the risk assessment?
Yeah.
Okay.
Please, yeah, please.
Okay, so first of all, I should say that this is not my presentation. This is a program that was done by ICF for the state of California. Hold on.
Actually, Efrat, we have 55 participants still in our webinar, and no one wants to leave. Yeah,
no one wants to leave. Okay,
yeah.
That's fine. So I'm just mentioning this is not a program I created, but if you remember our conversation from earlier in the week, climate risk and vulnerability assessments are done differently at the sectoral level than they are. Each sector has to develop its own methodologies and different approaches. So California is very advanced in the US in terms of how it looks at climate change and how it's incorporating climate change. And it has required all of its public utilities to provide the state with climate adaptation plans for the company, at the company level, right? So this is not at the district level or region level or city level. This is already at all companies above a certain size are required to already provide and show that they're adapting to climate. So they started looking at what are the issues for the electrical grid, for the energy grid. So this is Southern California, because California has 3 grids, but this is Southern California grid. So they developed 3 scenarios. The grid in Southern California is hydropower from the Colorado River to generate electricity, and natural gas and some nuclear, but the nuclear power plants are being decommissioned, so that wasn't considered in this assessment, because the expectation is that within 7 or 10 years, all the nuclear power plants in Southern California are going to be out of business. They're closing them down. They started closing them down after Fukushima. That was a very clear directive, so they've just started decommissioning them. So they developed 3 scenarios for the experts developed 3 scenarios to look at for challenges to the system is facing. One is periodic flooding. The second is long-term flooding in the sense of continuous flooding that creates a long-term event like a hurricane. And long-term chronic flooding, such as sea level rise, that creates continuous low-level flooding. And what you see on the right hand, the simultaneous 12-hour loss of 12 substations, simultaneous loss of 2 weeks of power at 4 substations. This is sort of what they estimate would be the threshold level at which the stations would start, or the network would start showing problems, or would start having problems balancing the energy use across the system. So they did assess all the assets along the coast. And they found out that the problem is mostly in the distribution systems and not in their transmission systems. They have some problems with the transmission, but it's mostly distribution, that they're older, they're more vulnerable to direct impacts, and apparently they're less well maintained. So as you can see, they basically mapped every single system, substations mostly, but also electrical poles along the network, to find out which ones are problematic for up to 5 meters of sea level rise and up to 2 meters of sea level rise. Up to half a meter of sea level rise is probably the average size of the expected damage. And then they costed that out of in terms of millions of dollars on those two scenarios. Cost of, if you remember our discussion that from the other day, when we talked about, you need to find the right parameter to compare adaptation options, otherwise you get very skewed results. So what they were looking at is not the cost of replacing facilities, but the cost of not providing energy or electricity to households. So basically they were looking at loss of service as the key parameter, as opposed to the cost of replacing the facility or asset. And then they found basically that they had 13,000 customers at risk. And this is what it falls apart, what was included in this. So we had sewage pumping stations were part of this area, hospitals were part of this area, one airport, shipping port, and a naval yard, a military installation. So basically 13,000 private customers plus public level facilities would be impacted by half a meter of sea level rise. This is something that I will be talking about more when we talk about infrastructure, but adaptation pathways are a really good for long-term facilities that take, for infrastructure that has both a long time to plan and costs a lot and takes a long time to implement. Adaptation pathways are a really useful way of figuring out how to position and when to bring facilities into play. And we'll talk more about this on the infrastructure workshop. But basically, each circle reflects a decision point where you can bring in a facility. So you can do a threshold assessment, but very soon, let me see if I can get the annotation going. But very soon, you see right here, it stops becoming effective. Whereas all the other options, you still have an option of coming in at different ways and connecting. The current policy will run out within, let's say, 20 years, will reach a dead end. And if you don't change the policy now, within 15, 20 years, you will reach a dead end and there will be no way to expand it and fix it. But you can see that some sections are more connected. Some things like grid enhancement don't kick in until 10, 15 years down the road, whereas cost benefit analysis at some point becomes irrelevant because, yeah, it's costing you now, but if you don't do it now, then you're not going to be able to do anything else. And at some point, you know, on an asset that takes 30 years, if you wait 20 years to make a decision, it doesn't even matter anymore, right? You have to go for whole cost replacement as opposed to partial incremental improvements. Anyway, like I said, we'll talk more about this when we talk about infrastructure, but I just wanted to show you how some of this works. For the gas network, they ran the same kind of exposure, and they basically found that 1% of their gas network a pipeline really was exposed. it's mostly limited because the pipelines are buried, but where it crosses water, everywhere where you have essentially a gap in the land is where you have a weak point because of erosion that would erode the support, and the pressure would change under the buried pipelines. And then they also, given that this is California and wildfires, as we discussed, are becoming much more critical, they also ran a wildfire scenario on how many of their assets would be damaged by wildfires. And you can see that there's some areas that are not at risk at all, but some areas at risk both from coastal flooding and coastal pressures, as well as from fires such as Oceanside, which is anyway, Oceanside is up here on above Escondido. Extreme heat, which is air temperatures, they checked where they have facilities that are more risk, and you can see the inland areas are at more risk for that. Inland flooding was also looked at. This comes up to about, just so you understand, this took about 3 years to do, to collect all the data and to do all these scenarios and do this. This is not a 3 months report, and there are about 8 or 9 volumes of this major report. Given that this is California and we have a lot of earthquakes there, they also did assessment for earthquake damage, which facilities are located near earthquake zones or at risk. Market considerations, same thing as we did with the electricity. They looked at what happens with the gas policy, and you can see here that the current policy actually has a dead ends much sooner for the gas policy than it does for the electricity policy. It means it's overall it's a lot less robust than their approach to the electrical grid. So that is something that they have now started revamping because they identified this as a very weak point. Sorry. Okay, that's it really. So any questions?
Oh, thank you, Efrat.
You're welcome. I was very fast, I know, but I just wanted to show a couple of examples to supplement the amazing presentations that were done earlier that I thought were really informative.
Yeah, very informative webinar today, and people are writing that it's too much information and it's difficult to cope with the mind. But we have still one question in the chat. From Vladimir Shatocha. I think this question is for all the speakers, for all the experts, for their opinion. Vladimir, are you with us? Do you want to read this question?
Yes, I'm here.
Yeah, okay. We are happy to see you.
Well, it's a bit more complicated. Yeah, I will try.
I mean, your question.
I'm here. Yeah. Sorry, I was not prepared for that. Yeah.
But it's
so the
very
question
nice
is that first of all, many thanks for very interesting presentations, and I learned a lot today. But my question is that it can happen that all of a sudden we may have not enough of energy to cope with the climate change. For example, to pump the water in the Netherlands due to ocean sea level rise, or to cool buildings in Ukraine or in Florida, whatever. So our demand for energy may grow just because of this of the climate change, and some researchers say it can grow quite substantially, and it's apart from the need for more energy due to socioeconomic development. Shall we take it into account in, is it a part of adaptation of our power sectors that we have to take into account that the demand for energy can grow in future?
Absolutely. You should take that into account, and you should also take into account reduced resource availability, and to see how much your system or your grid needs to be stretched or needs to be made more flexible. The key for adaptation, I think, especially for systems such as energy, which have a lot of hard assets, is to reduce the number of points of failure in the system, right? And increase not only its overall efficiency, but also to reduce the pinch points, the points where the system is going to fail. Because we don't quite know, how well we know the theory, we know the models, but each country is different for its own individual socioeconomic reasons. So you should always not only look to expand the system so that it has internal backups, and by internal backups, I mean that you don't rely just on one energy source, but also that you don't have one point of failure in the system, so that if you're not maintaining your hydro plants, you still have enough solar energy to meet your needs, or at least fill in temporarily some of the things. If your pipeline collapses because of whatever, then you can still use an alternate method, whether it's distributed generation or storage, batteries or hydropower or other transmission lines to provide energy to your people. So yes, you need to take into account both socioeconomic growth, but also changes to projected climate.
Yeah, thank you.
Thanks a lot to Vladimir. Thanks a lot to Efrat. So, dear friends, dear colleagues, do you have more questions, or should we finish for today and continue in the future?
If I may, I couldn't find the button, raise the hand.
Okay, yeah, Galina, we are here. Hear you well.
Oh, okay. Hello. I would like just to add a few thoughts or few reflections on the presentations of previous speakers. For instance, Mrs. Loretta, before the lunch break, in the end of her presentation, mentioned these points about the water and land and energy issues. I'm interested in the part of water and energy nexus. So it's already known at the moment that renewable energy, especially solar and wind, they require much less of water than fossil energy does, especially the nuclear and CHP. So nuclear and CHP require significantly more water to produce energy, whereas renewable energy such as solar, wind, they require less water. For instance, wind doesn't require water at all, whereas solar requires water for cleaning and for maintenance of the solar panels, and that's it. So, and now Ukraine is trying to define the way how, or to see how we can increase the share of renewables, or what we can do with the available thermal power plants. But I guess that, and we already heard a lot of adaptation measures for different type of technologies, especially for energy output. But I think that the question that the decision is already there in place, meaning that once we have more of renewable energy, we will definitely need to transmit it, but still, once we choose it, we will gain in some other aspects, for instance, water use. Yeah, this was the thought about Loretta presentation, and then later, in a presentation of Mr. David, he mentioned that biomass potential and contribution in Ukrainian energy system could increase by 2050. It's already a good thing. But at the moment, biomass for energy purposes is significantly underutilized in Ukraine, which is a bad thing. I really don't think that the technologies, particularly in biomass, will significantly change by 2050, because as we can see for thermal power, the technologies for heat production in biomass, they do not change significantly. I mean, the types of boilers, they are pretty much the same. But what could expectedly change is the biofuels if we continue to use them. I mean, the advanced types of biofuels and so on. So my point is that we don't have to wait for extremely new and brand new technologies in biomass. They are more or less available and known at this moment. And also my thought about Ms. Sophia's presentation, that and she mentioned that let's say fast trade of electricity across Europe is let's say one of adaptation measures, quite indirect, I would say. And Ukraine, I just wanted to mention that Ukraine is now trying to join the NSOE to make sure that the electricity could be traded to Europe as well, because now only a small part of Ukraine is connected with Europe via the Burштyn Energy Island. But hopefully when the certification of transmission system operator and other technical and institutional requirements will be done, then Ukraine will be able to join the NSOE, and we would be Ukraine would be able to benefit of trade with Europe. Yeah, that's all I wanted to say. Thank you.
Thank you, Galina, for feedback. Actually, Loretta already left our webinar for today, but we will send her maybe these feedbacks, and we will take the presentation from all the speakers to comment it while having our discussions in sectoral groups also. Dear participants, do you have more questions or reflections about the webinars or presentations for today? Дорогі учасники, чи є у вас ще побажання задати якісь запитання чи уточнення до наших спікерів, до експертів?
May I say a few words? Here is Andriy Demidenko.
Yeah, sure, Andriy. I started to worry. Where are you?
Don't worry, I'm okay. This is not my favorite sector. When you will speak about water resources, believe me, I will not be that shy.
Okay.
I would like to say thank you to many of speakers and to you personally for this very good, facilitation. But my question is, my impression is, as a scientist, I'm very much interested in these results. But most of these, activities are so far from the, interest of our decision makers. And maybe scientists, I don't know that much energy science, but regarding many other things, it is really too far. It is very interesting for me was to listen in, but I would like to know, replies and reaction of those other who are members of our working group, as well as other participants, which is 50 or still 50. What is their impression? I think it will be very useful, at least for me, at least for those who are in charge of further work on strategy and especially on National Plan for Adaptation. Thank you.
So this is Efrat. I don't think this was scientifically oriented at all. The IEA is very focused on providing very practical solutions. If you read their documents, they're very focused on practical changes to the grid. The Netherlands, even though it was presented as research, they have changed their grid. They have put in quite a lot of changes into their grid because of these kinds of tests. So it's not so much that it's research. I think I think this is where, and I know at least in the US, the changes are happening at an individual state level. While Trump was in office, under Obama, they happened much more quickly because they were tied to incentives to the industry. Biden will now reinstate those, but basically, once the data is there and you can figure out how you're redoing the grid, it takes time to plan a new energy grid and to change the loads and to change the facilities, because a lot of energy facilities have a 30 to 50 year life period. So design life. So if you have a system that's 20 years old, unless you destroy the facilities that you have right now and rebuild and build new ones, you're not going to see fast change. But if you have systems that are in place since the 1930s or 40s, you will see much faster change, just because these systems are you have to close them anyway because they're at the end of their life. So I don't know where the Ukrainian system is in terms of its design life averages. I suspect you have probably a mix of things. And you see faster change in the older systems and in areas where you have fast population growth, just because the system can't keep up with existing designs. This is happening all over the world, right? But once you know what the data is, you can inform the load distribution, you can inform the energy supply, you can put in the supporting systems, whether they're wind or solar or other biomass or whatever, so that they're ready to pick up as soon as you start decommissioning some of the older plants. This requires a very in-depth and technical look at what your systems are, how old they are. Not only, power poles you replace every 10 to 15 years, right? Transmission lines you replace every 5 years. Power plants you replace every 50 years or 30 years, depending on the type of power plant. So you have to understand what the mix is in Ukraine, what the facility mix is, as well as the energy mix. This is one of the things that makes the energy sector so difficult. You need to not only to plan the technical mix, but you also need to plan the infrastructure development and development of new power plants, especially big ones. It takes a lot of years. It takes about, between 2 and 5 years just to design them. It takes, 3 or 4 years to build them. And then they last 30 to 40 years. So you have a very long lead time that you need to plan. So if you want to change in 10 years, you need to start planning now. And that's why it's so important to have and start doing the research now, so that Ukraine is ready for when it does need to change some of its plants. I mean, if you built a plant in the 1980s, it's not going out of business for another 20 years at least.
Great, Efrat. It's great. I can't say more, but may I have practical question? I know nuclear energy sector better than any other, just I'm physicist. And I could tell you that, for example, a very good example, which was in the very beginning by a representative of EU delegation to Ukraine, that the main bottleneck for development of nuclear, and not only nuclear energy, is the absence of water for cooling. I can tell you that among many decision makers, it is rather rare, this understanding. They're absolutely sure that bottleneck is somewhere. They could develop a nuclear energy sector as they wish, irrespectively to the fact that even 30 years ago, it was clear that Ukraine has not enough water just for cooling. Not only, but in nuclear energy, it's sometimes more visible than in other sectors. But just simple.
Well, you know what they say to
is not well known to decision makers and to public. That's what I'm saying about that. Regarding technical presentation, it's great. But for whom is this? I don't see anybody on our side. Maybe I'm wrong. Maybe there are some other people from energy sector, but I didn't see their contribution to the development of adaptation strategy. It is not an issue. It is not a water issue for adaptation of energy sector, while the water issue is the main question for adaptation to climate change in energy sector. That's what I'm talking about. And that's why I ask maybe some other, not from your side overseas, say about, but among those who listen to your and other presentation, what is their opinion from that point of view? Sorry for so long intervention, but it was permanently my concern during brilliant presentation. Thank you to all speakers.
Okay, yeah.
Я можу повторити
hard.
українською мовою,
But
колеги
this
з
is,
України.
but Andrei, if this hasn't been addressed in previous power plans, then your adaptation plan for the power sector, for the energy sector, that's what it needs to address. That's part of what it needs to start saying and start to include. This is, but the adaptation plan hasn't been developed yet. So whatever comes out of this process, which is just the beginning of thinking of adaptation in the energy sector, needs to start considering these constraints such as water. Yeah.
Development of the whole nuclear energy sector in Ukraine has this understanding that water is a bottleneck, is a main constraint. That's what I'm talking about. Water, not something else. First problem. And може я повторити українською мовою? Як щодо моїх колег, які слухали, чи для когось це дійсно з енергетики, це дійсно важливо для розробки стратегії, чи можливо планів, чи планів адаптації стратегічного сектору, бо я все ж таки з іншого сектору. Дякую.
Ну, наскільки я знаю, що у нас досить багато енергетиків, чи мене зараз чутно так, у нас дуже багато енергетиків саме з енергетичних компаній реєструвалися на вебінар. І також вони отримають запис цього відео. Я принаймні сподіваюся, що вони і частково присутні і ознайомляться також з цим. І крім того, хотіла нагадати, що у нас ж плани з адаптації секторів, власне, ще не розпочалися, тільки от розпочинаються. Так що, будь ласка, не дивіться на це зовсім безнадійно. Я сподіваюся, що все, що зараз от було розказано, показано, такий, нехай це поверхневий огляд. Так, тут нехай це такий попередній поверхневий огляд сектору енергетики, але все ж таки, бачите, він досить ґрунтовний, багато колег виступили з величезними презентаціями. Це все можна буде використати і вкласти в ці плани, в ці секторальні наради, які ми плануємо ближчим часом, починаючи з весни.
Пані Ольга, доброго дня. Працює мікрофон?
Доброго дня, Оксана.
Працює мікрофон, бо в мене було проблеми звука.
Так, зараз чуємо вас нормально. Раді вас чути, принаймні, якщо не бачите.
Шановні колеги, пане Андрію, відповідаю на ваше запитання. Можливо, це більш вузький кейс, якщо вам цікаво, я тоді надам такі приклади. Ми на рівні міст в рамках угоди мерів, коли розробляємо плани дій сталого енергетичного розвитку і адаптації до змін сектору, ми розглядаємо компонент енергетики і от вразливість цього сектору, які заходи саме от міста можуть робити в цих питаннях. Тобто на рівні країни, на рівні міст. Зараз, можливо, такі кейси на рівні більше інфраструктури, це центральних теплових систем, і зараз дуже активно з приводу водоканалів. Ну, тобто, якщо вас такі кейси цікавлять, я вам окремо потім можу надати. Дякую.
Armenia can make some remarks for this question, if possible.
Yeah, sure.
So, first of all, about development of renewables, means solar and wind. That is can be mathematically based. It can be no more than 50% of production, because, for example, solar energy can produce in daytime, but it's consumption in evening and night. Do you need reserve capacities for covering this energy consumption demand? Of course, problem can be solved by batteries, but batteries is a very, very expensive installations. can be constructed PSP plants. It also not so cheap option. Then 50% for different countries, it will be okay. Second one about the development of nuclear and problem of water. Let me say that modern technologies, for example, combined cycle plant in Armenia, even don't have a cooling towers, and only using for cooling so-called radiators, and no cooling towers, especially wet cooling towers. About nuclear, now if my colleague want contact with me, I can provide him the report of atomic agency about solve this problem. In means instead of the main demand of water, it's cooling water, which using in wet cooling towers. But it's recommended the using the dry cooling towers, or which don't use for cooling water. That can be in my country existing the plants, thermal plants, which is using these dry cooling towers. It's called Heller towers. And then, do you need too much water for operation of nuclear power plant, especially for cooling? If you want to have some reports about it, I can provide to my colleague. But let me mention that this dry cooling towers is very, very expensive. So thank you.
Okay, thank you very much. And yes, sure, we would be grateful for all the materials that you would like to pass. And you can contact us, and I will write the email for communication in the chat now. And we will put all the materials in our Gmail connection, so everybody can have the access to these materials. Thank you. And dear colleagues, now we have to finish, and I would like to pass the final word to Andreas Bierman. Andreas, please, the stage is yours.
Yes, thank you very much, Olga. So I think this has been a really valuable discussion, and I certainly have come away and learned a lot from it, and I hope it's the same for everybody else who participated. I think it's quite clearly showed what I suspected would be the case, and noted in my introductory remarks, that there is a clear adaptation challenge for energy in Ukraine that needs to be addressed. And getting that sort of confirmed by the technical experts has been really, really valuable. So I would like to thank everybody for their participation today. I hope that, similar to me, you've been able to take something away from here. And we really all look forward to working with you on the continued development of the National Adaptation Strategy and the sector adaptation work that is necessary to get Ukraine prepared for climate change, which unfortunately I think can no longer be avoided. So thank you very much, and I'm sure I'll see you again in other workshops and forums in the future.
Thank you, Andreas. Thank you, everybody. I thank all the speakers for today, for interesting presentations and for your involvement in this process. And you can see the email for communication and for sending all the materials in the chat. And see you next time at 12th of February for all the participants who are interested in health protection programs. Thank you. And bye-bye.
Thanks so much. Bye-bye.